In the silent darkness beyond our telescopes, in the obscure reaches of the night sky where casual eyes seldom drift, there exists a flame, burning, seething, and radiating a quiet fury. It is not a flame of fire, but one of stars and dust, of ancient light and newborn chaos. This is the story of NGC 2903, a galaxy ablaze not with violence from cosmic collisions or galactic warfare, but with the unrelenting birth of stars erupting from its heart. And yet, this flame, this beacon of activity, remains one of the universe's best-kept secrets. But before we continue, subscribe to the channel so you don't miss out on any of these videos. Imagine staring into the constellation of Leo, a region of the sky familiar to stargazers and astronomers alike. Nestled quietly within its boundaries is a galaxy that rivals the beauty and size of our own Milky Way. But you won't find it in the Messier catalog. You won't find it adorned with the same fame as Andromeda, the Whirlpool, or the Sombrero Galaxy. NGC 2903 has somehow slipped through the fingers of popular astronomy, overlooked by one of history's most renowned sky surveyors, and passed over in mainstream cosmic conversations. And that's part of what makes it so remarkable. It's a treasure hidden in plain sight, a diamond glowing just beyond our historical awareness. The deeper you look, the more NGC 2903 reveals its secrets. At first glance, it might seem like just another pretty spiral, an elegant arrangement of arms winding around a luminous center. But behind that optical elegance lies something far more violent and dynamic, a galactic heart that is undergoing a furious starburst, an event so intense that stars are forming at a rate far higher than normal. This isn't a passing phase, nor is it caused by recent trauma from a galactic collision. It's something that seems to come from within, driven by the galaxy's very structure. And that's what makes it not just beautiful, but essential. Barred spiral galaxies like NGC 2903 play a crucial role in our understanding of galactic evolution. These galaxies possess a central bar, a stretched stream of stars, that acts like a highway for gas and dust, directing it inward toward the galactic core. This motion feeds the core like blood rushing to a beating heart, fueling the starburst and shaping the very future of the galaxy. What happens in the bar, and more importantly, what happens in the core, reveals a great deal about the forces that sculpt the cosmos over billions of years. But what makes NGC 2903 particularly poetic is not just what it is, but what it is not. It is not interacting with other galaxies. It's not in a crowded galactic cluster. It's not undergoing gravitational chaos. In many ways, it's isolated. And yet it thrives. The fire at its center has been kindled not by external collisions, but by internal orchestration. It is the perfect example of a galaxy feeding itself. And in doing so, it becomes a living laboratory, a cosmic specimen preserved in deep space, waiting for us to unlock its rhythms and read its story. Astronomers adore it. Telescopes return to it again and again. It is nearby, by cosmic standards, only about 30 million light-years from Earth, making it a relatively close target to observe in detail. And yet, NGC 2903 doesn't scream for attention. It hums. It burns quietly in the dark, its light bleeding into space as its stars are born, live, and die, cycling through the cosmic rhythm that defines all galaxies. There's something almost mythical about a galaxy like this, hiding a furnace behind graceful spiral arms, its brightest truths shrouded in gas and dust only visible in certain wavelengths. Observing it is like listening to a whisper in the vast cathedral of space. You must know where to look. You must be willing to listen. And when you do, what you find is not just data or images or spectra. You find a story of energy, isolation, structure, transformation, and time. NGC 2903 may not be famous. But perhaps that's the point. It is not the celebrity of the universe, it is the unsung hero. It is the quiet blaze in the Lion's constellation, hiding its furnace beneath veils of stars, beckoning us to pay closer attention. If you were to trace the outline of the constellation Leo, the celestial lion, on a clear night, your gaze would follow the majestic arc of stars that form its signature backward question mark, the sickle, leading down into the lion's body and tail. It's here, in the lion's flank, not far from the bright star Regulus, that something extraordinary resides. Not visible to the unaided eye, not whispering for your attention like the brighter galaxies of the night sky, but rather resting quietly in the dark like a glowing ember, NGC 2903. This galaxy lies some 30 million light-years from Earth, a distance that humbles the imagination. Light, traveling at the fastest known speed in the universe, takes 30 million years just to reach us from this cosmic neighbor. When we see NGC 2903, we see it not as it is now, but as it was long before the first humans painted animals on cave walls or even before our ancestors walked upright. What reaches us is a message from the past, a record of ancient stellar processes still unfolding today. To find it in the sky, astronomers look toward the northern hemisphere's spring constellations, specifically Leo, which becomes prominent in the night sky from February through May. Leo is a constellation rich with galaxies, as it sits in a part of the sky pointing away from the plane of the Milky Way and toward the deeper cosmos, where galactic clusters and fields of isolated galaxies begin to emerge. NGC 2903, though not a member of any major group, floats in this celestial realm, isolated but not alone. It's positioned just below the lion's mane, more specifically, a few degrees south of Lambda Leonis and the arc of the sickle. For amateur astronomers, it's a rewarding target in the right conditions, visible through mid to large-sized telescopes, appearing as an elongated smudge with a bright central core and faint spiral arms extending outward. But its full beauty and structure are only revealed through deeper imaging and long exposures, tools that let us peel back the layers of distance, dust, and time. Its coordinates place it at right ascension 9 hours 32 minutes and declination plus 21 degrees 30 foot. These numbers, while technical, lock it into the cosmic address book, making it a reliable fixture in the celestial landscape. And unlike many galaxies that live within dense clusters or gravitationally bound groups, NGC 2903 enjoys a kind of solitude. It's not battling with nearby galaxies, nor being stretched or warped by tidal forces. It hangs, suspended, in a relatively open patch of space, allowing its structure to remain pristine, an undisturbed template of spiral architecture. This location, both in space and in the sky, grants NGC 2903 a dual nature, close enough for detailed study, but obscure enough to remain overlooked by casual stargazers. Its proximity means astronomers can resolve fine details, individual star-forming regions, dust lanes, even movements within the core, but its subtle glow means it's often bypassed in favor of more luminous or well-known galaxies. Yet this very quality, the quiet brilliance, the isolated position, gives it a special kind of purity. It is unspoiled by the gravitational chaos of neighbors. It's a galaxy writing its own story in the void, under the watchful gaze of Leo's stars. And if one were to imagine standing on a cold mountaintop, telescope trained on this faint spiral millions of light years away, it would feel like eavesdropping on a secret, a cosmic furnace humming silently in the wilderness of space. Despite its shimmering presence and relative brightness in the sky, NGC 2903 has a strange relationship with fame. It shines with a magnitude of around 9, which makes it a prominent enough object in the realm of deep sky observing. For comparison, many objects in the Messier catalogue, those sky treasures compiled by French astronomer Charles Messier in the 18th century, are dimmer or more diffuse. And yet, NGC 2903 is conspicuously absent from that celebrated list. This omission isn't due to some flaw in the galaxy itself, nor a lack of brightness. Rather, it has everything to do with timing, geography, and intent. Messier's goal was never to catalogue the most beautiful or scientifically interesting objects in the night sky. His aim was practical. He was hunting comets. In doing so, he often encountered fuzzy, unmoving smudges of light that looked suspiciously like comets through his relatively small telescope. To avoid being misled, he began compiling a list of these imposters, non-cometary objects that might trick comet hunters into wasting their time. In this context, NGC 2903 was simply in the wrong place at the wrong time. Located in Leo, it sits relatively low on the horizon from Paris, especially during the months Messier was most active. Atmospheric distortion and limited visibility near the southern horizon would have made spotting it quite difficult with 18th century optics. Even if Messier had known something lay in that region, the tools at his disposal likely wouldn't have captured the full glory of the galaxy, just a faint blur, easily dismissed in the search for transient comets. Moreover, his catalog only extends to 110 objects, and while it includes some stunning galaxies, like the Whirlpool, M51, and the Andromeda Galaxy, M31, many of his entries were more influenced by their position in the sky and their likelihood to be confused with comets. NGC 2903, while bright and structured, is relatively compact in appearance through small aperture telescopes. It wouldn't have stood out as an obvious threat to a comet hunter's ambitions. Even after Messier, NGC 2903 remained somewhat underappreciated. It wasn't until William Herschel, a later and more ambitious surveyor of the night sky, swept through the region with his vastly superior telescopes that NGC 2903 was officially recognized and catalogued. Herschel noted its brightness and spiral structure, and it was later catalogued in the New General Catalogue, hence the NGC designation, but by that time, the public's fascination was still largely tethered to Messier's list. Astronomy popularizers, telescope manufacturers, and star guides all focused their energy on those 110 entries, creating a kind of greatest hits mindset that persists to this day. As a result, NGC 2903 became something of a hidden gem, known and loved by seasoned observers and professional astronomers, but largely ignored by casual stargazers. You won't find it on many beginner astronomy posters or in children's books about space. Its name doesn't roll off the tongue like Andromeda or the Sombrero Galaxy. But this lack of mainstream attention doesn't reflect its scientific importance or its visual impact. Ironically, its absence from Messier's catalog has helped preserve a certain mystique. Unlike M31 or M42, which are almost too familiar to provoke wonder anymore, NGC 2903 retains an aura of discovery. For those who stumble across it in a telescope, it often feels like a personal secret, a bright, swirling galaxy lying quietly just beneath the lion's mane, ignored by the guides but radiant in the eyepiece. Astronomers today appreciate NGC 2903 not only for what it reveals about galactic structure and star formation, but also for what it represents, a reminder that the cosmos still holds brilliant secrets, even in the most charted regions of the sky. It's a cosmic irony that one of the brightest non-Messier galaxies visible from the northern hemisphere never made it onto the list that shaped public astronomical awareness for centuries. But in that oversight lies an invitation, for the curious, for the patient, for those who seek the light just beyond the familiar stars. To understand the true nature of NGC 2903, we must step beyond casual observation and into the realm of galactic classification, where form meets function, and where shape speaks volumes about a galaxy's inner mechanics. NGC 2903 is officially classified as a barred spiral galaxy, with the specific designation SBBC. This seemingly cryptic combination of letters, SBBC, is more than just a label. It's a window into the physical structure, dynamic processes, and evolutionary stage of the galaxy itself. The Hubble sequence, devised by Edwin Hubble in the 20th century, remains the dominant framework used by astronomers to categorize galaxies. In this system, galaxies are divided into broad categories, ellipticals, spirals, and irregulars, and then further refined based on specific features. Spiral galaxies are given the label S, and if they possess a central bar, a stretched linear structure running through the core, they are marked with a B, becoming SB. This is where NGC 2903 begins, with the foundational architecture of a spiral galaxy, but enhanced by the presence of that crucial bar. Now, the spiral subclassification continues with the lowercase letters A, B, or C, which indicate the tightness of the spiral arms and the prominence of the central bulge. An SBA galaxy would have tightly wound arms and a large central bulge, whereas an SBC would display loose, sweeping arms with a smaller central bulge. NGC 2903, as an SBBC, falls neatly in between. It shows moderately tight arms, not too rigid, not too chaotic, and a core that, while noticeable, is not dominant. This transitional label, BC, captures its dynamic balance, a galaxy in an active stage, neither young nor old, either tightly constrained nor completely free-flowing. Visually, this means NGC 2903 appears as a broad disk with a strong linear bar running through the center. The bar itself is composed of billions of stars, older, redder stars, tightly packed in a stellar stream that acts like a gravitational bridge across the nucleus. This bar is not static. It rotates, slowly, like a cosmic turbine, and in doing so it exerts powerful gravitational torques on the surrounding gas and stars. This rotation doesn't just stir the pot, it directs traffic. Gas clouds that would otherwise orbit aimlessly within the disk are pulled inward, channeled by the bar toward the galactic center, where star formation activity is triggered on a massive scale. In this way, the bar is not merely decorative, it's a driver of evolution, a dynamic funnel that reorganizes the galaxy's internal structure. Spiral arms emerge from the ends of this bar, curling outward like tendrils of smoke, populated with young blue stars, star-forming regions, and intricate lanes of interstellar dust. These arms trace the movement of density waves, regions of higher gravitational concentration that propagate through the disk, gathering and compressing gas as they go. Wherever these waves pass, star formation blooms like fire trailing the wake of a match. The spiral pattern isn't carved into the galaxy like grooves on a record. Rather, it's a living, moving structure, a pattern imposed on the flow of material, constantly evolving yet persistent over cosmic time. NGC 2903's arms are relatively symmetric, which is notable for a galaxy in isolation. In many spirals, asymmetry is often the result of gravitational interactions with nearby galaxies, nudges and tugs that distort the arms into strange, lopsided shapes. But NGC 2903, without known satellite galaxies or obvious companions, seems to maintain its form largely through internal forces. This makes its well-balanced arms an even more remarkable feature. Their structure is both aesthetic and functional, serving as the grand conduits for star formation and angular momentum redistribution. The bar itself is estimated to stretch across tens of thousands of light-years, nearly a third of the galaxy's total diameter. It's not just a central decoration, it's a keystone feature. The dynamics of this bar influence the galaxy's entire ecosystem. By funneling gas inward, it initiates a cascade of processes. Molecular clouds become compressed in the dense inner regions, triggering the collapse of gas into protostars, lighting up the core with new stellar energy. In fact, one of the most striking consequences of this inflow is the starburst region located at the very heart of NGC 2903, a blazing furnace of stellar birth we'll soon explore in greater depth. But for now, it's important to appreciate how the SBBC structure contributes directly to this phenomenon. The barred nature, the SB, is what initiates the inflow of material, while the intermediate spiral type, the BC, suggests a well-developed disk and star-forming arms without the extreme tightness or looseness of the outer categories. It's the perfect recipe for controlled, sustained starburst activity. Not chaotic, not stagnant, but alive, pulsing, rotating, feeding itself like a flame fed by its own oxygen. Beyond its visual appeal, the structure of NGC 2903 carries implications for galactic evolution. Bars are not permanent features. They are thought to form later in a galaxy's life, emerging from instabilities in the rotating disk. As a galaxy matures, its inner regions become denser and more organized, and in some cases, a bar structure emerges as stars migrate into elongated orbits. This makes NGC 2903 a relatively evolved system, not primordial, not embryonic, but in a state of robust middle age. The bar may grow stronger over time, or it may eventually dissolve, depending on the galaxy's interactions and internal feedback. But at this moment, it serves as both the architect and the engine of the galaxy's ongoing transformation. And so, this classification, SBBC, is not a cold scientific label. It's a diagnosis, a status update, a poetic descriptor of a galaxy in motion. It tells us that NGC 2903 is a balanced spiral, a structured system, a galaxy organized around a linear core that doesn't just support the galaxy's form, it fuels its flame. Every curve of its arms, every grain of dust, every glowing star-forming region has been sculpted by this architecture. To look at NGC 2903 through the lens of classification is to glimpse the inner symphony of a galaxy that is, quite literally, built to shine. If one could fly across the great disk of NGC 2903, past its sweeping spiral arms and deeper into its luminous heart, a remarkable structure would emerge, stretching like a glowing bridge across the galaxy's center. This is the central bar, the elongated spine of stars that defines the very essence of NGC 2903's dynamic life. Far from a static feature, the bar is a gravitational powerhouse, a galactic engine channeling material inward, sculpting the flow of gas, and reshaping the future of the galaxy from the inside out. Stretching across nearly 20,000 to 30,000 light-years, the bar of NGC 2903 is made primarily of older stars, mature, reddish stars that no longer burn as hot or bright as the younger blue stars populating the spiral arms. These stars are packed densely together, moving along elongated orbits that twist through the gravitational landscape of the galaxy's core. At first glance, the bar might seem like a calm, stable formation. But look closer, and you'll see that it's alive with motion, a conveyor belt of material, constantly rotating, constantly stirring the pot of the galactic core. This bar isn't a passive feature. It exerts gravitational forces that disrupt the circular orbits of gas clouds and stars within the galactic disk. These disruptions trigger a process called angular momentum transfer, in which gas is robbed of its rotational energy and gradually pulled inward along the length of the bar. The bar acts like a funnel, one end catching gas and dust from the outer galaxy, the other end delivering it straight into the central region. It's not a gentle process. This inflow compresses the material, heats it, and increases its density to the point where star formation ignites. Imagine, then, the bar of NGC 2903 not as a quiet bridge, but as a blazing avenue of energy, streams of gas coiling along invisible gravitational highways, colliding, compressing, and collapsing into new suns. This mechanism turns the bar into a dynamic channel, feeding the firestorm of stellar birth that rages in the core. And all of it happens on a galactic scale, light-years across, millions of solar masses of material, all flowing inward under the orchestration of this central structure. Observations in multiple wavelengths reinforce this vision. In optical light, the bar is visible as a bright, elongated feature bridging the central bulge. In the near-infrared, where dust becomes less obscuring, the full extent of the bar emerges more clearly, showing a smooth distribution of old stars that extend beyond what the eye can see. In radio wavelengths, tracers of cold gas like carbon monoxide reveal long streams of molecular clouds coiled along the bar's length, being drawn inexorably toward the center. And it is this combination, stellar mass, cold gas, and gravitational dynamics, that turns the bar from a structural element into an evolutionary force. Within this framework, the bar is not only transporting raw materials, it's also setting the stage for complex feedback processes. As gas reaches the core and ignites in rapid star formation, massive young stars quickly evolve and die, releasing winds and supernova explosions that blow material outward again, creating turbulence. The bar thus sets up a feedback loop: gas flows in, stars form, energy is released, and the cycle begins anew. This feedback helps regulate the rate of star formation, preventing it from becoming so intense that it burns through the galaxy's fuel in a single cosmic heartbeat. Another crucial aspect of the bar's influence is its ability to create resonances, zones in the galaxy where the rotational speed of the stars and gas aligns with the patterned speed of the bar. These resonances, especially the so-called inner Lindblad resonance, ILR, act as gates that channel gas even more efficiently into star-forming rings or nuclear disks around the very center of the galaxy. In NGC 2903, such resonances may play a key role in organizing the inflow of gas and sculpting the spectacular activity in the central starburst region. But the bar's influence doesn't end at the center. The very act of funneling gas inward robs the outer galaxy of star-forming fuel, which has implications for how the spiral arms evolve over time. In this way, the bar helps redistribute not just material, but destiny, deciding where stars will form, where they won't, and how the galaxy's light will change in the future. It acts both as creator and destroyer, concentrating energy in the core while gradually quenching the periphery. Galactic bars like the one in NGC 2903 also offer clues about the larger-scale structure of galaxies, including dark matter distribution. Bars tend to grow or dissolve based on the underlying mass profile of the galaxy. A strong, well-formed bar, as seen in NGC 2903, suggests a stable gravitational environment with significant mass in both the visible and invisible components. It hints at a dark matter halo that is massive but not too dominant in the inner regions, allowing the bar to form and persist without being disrupted. One of the most compelling insights about bars, particularly from simulations and long-term observations, is that they evolve. The bar in NGC 2903 may not have always existed. In its earlier life, the galaxy may have had a more traditional spiral structure with no central elongation. Over billions of years, as the disk became more massive and gravitational instability set in, the bar likely emerged, shaped by the self-organizing dynamics of the galaxy itself. And as time passes, the bar may grow longer, become more efficient at channeling gas, or potentially dissolve entirely, depending on how material continues to move within the galaxy. Today, though, the bar in NGC 2903 is in its prime, robust, active, and deeply influential. It stands as the central artery of the galaxy, a pulsating bridge between the majestic spiral arms and the frenzied starburst core. Through it flows the lifeblood of the galaxy, stars, dust, gas, and energy, all drawn inward by gravity, all reshaped by motion, all contributing to the glowing furnace at the heart of this remarkable system. It is a vivid reminder that galaxies are not static structures. They are dynamic, ever-evolving organisms, sculpted from within by features like bars that act as both architects and agents of change. And in NGC 2903, this central bar is not merely a curiosity. It is the driving force behind one of the most active, vibrant, and scientifically fascinating galaxies within our cosmic neighborhood. At the heart of NGC 2903, nestled within the gravitational grip of its prominent stellar bar, lies a region that defies the quiet dignity of the galaxy's serene spiral arms, a region so active, so incandescent, it can only be described as a starburst core. It's here, at this central juncture, that the galaxy's beauty erupts into a cosmic blaze of creation. While the outer arms spiral gracefully into the void, the core churns with fire, a stellar furnace where stars are born in vast, violent numbers, and where the galactic ecosystem transforms under the pressure of relentless formation. A starburst galaxy, by definition, is one that forms stars at an exceptionally high rate, often hundreds of times faster than a normal spiral like the Milky Way. In the case of NGC 2903, the starburst activity is concentrated primarily in the nucleus, rather than spread throughout the arms or triggered by collisions with nearby galaxies. This makes its core not only a marvel of astrophysics, but a prime example of secular starburst, a galaxy forming stars intensely from internal processes alone, without external provocation. Deep within the galactic nucleus, gas funneled inward by the central bar becomes trapped and compressed. As the material piles up in this central reservoir, gravitational pressure builds, causing vast clouds of hydrogen to collapse under their own weight. These molecular clouds, each potentially spanning dozens of light years, fragment into smaller clumps, each one the seed of a star. The environment here is extreme. Temperatures and densities rise, shock waves ripple through the gas, and newborn stars begin to ignite, flooding the region with radiation and powerful stellar winds. Infrared and radio observations, tools capable of peering through the thick veils of dust, reveal just how busy this core truly is. The rate of star formation in the nucleus is estimated to be multiple solar masses per year, with compact clusters of young, hot stars forming in tightly packed groups. These superstar clusters shine brightly in the infrared, hidden from view in optical light but unmistakable in their thermal signatures. The dust surrounding these clusters glows with re-radiated heat, signaling the presence of energetic newborns still wrapped in their dusty cocoons. Each new star adds to the cacophony, flooding the core with ultraviolet light, ionizing surrounding hydrogen gas, and creating vast H2 regions that glow in red and pink hues when seen in specialized filters. These ionized bubbles expand outward, often colliding with neighboring clouds and triggering a chain reaction of further star formation. It's a self-perpetuating storm, where one generation of stars sets the stage for the next. But this environment is not merely constructive, it is also violent. The most massive stars formed in the core burn through their fuel quickly, living fast and dying young. In mere millions of years, short by cosmic standards, they explode as supernovae, unleashing shock waves and enriching the surrounding space with heavy elements. These explosions are not isolated events. In NGC 2903's core, they happen with alarming frequency, sculpting the gas and stirring the interstellar medium into a turbulent froth. The combined energy of these deaths drives galactic winds, pushing material outward and sometimes halting further star formation in localized pockets, only for the cycle to resume elsewhere. It is in this dance, of inflow, ignition, death, and feedback, that the starburst thrives. Observations suggest the nuclear region contains rings of star formation, shaped by resonances induced by the rotating bar. These rings act like cosmic engines, taking in fresh material and lighting it up in waves of stellar birth. The tight, circular morphology of these rings is a key feature in understanding how NGC 2903 organizes its star formation, unlike the chaotic, widespread bursts in galaxies undergoing mergers. Zooming into the very center, beyond the reach of optical telescopes, astronomers have found compelling evidence of a nuclear star-forming disk, only a few hundred parsecs across, spinning like a tiny galaxy within a galaxy. Here, the density of gas and stars reaches its peak. The star formation rate per unit area is among the highest observed in nearby galaxies, rivaling those seen in more extreme starburst systems like M82, but without the external triggers. The stars born here often remain gravitationally bound, forming long-lived clusters that may persist for billions of years, miniature globular clusters in the making. This raises an essential question: how sustainable is this activity? Starbursts, by their nature, are temporary. They consume gas rapidly, and without constant replenishment, the fuel will run dry. In the case of NGC 2903, the presence of a large reservoir of neutral hydrogen in the outer disk, and possibly in a surrounding halo, suggests that this inflow may continue for quite some time. The galaxy could be feeding its core for millions of years to come, cycling material inward through the bar and allowing the central furnace to keep burning. And yet, the core's future depends on balance. Too much inflow and feedback mechanisms could blow out the star-forming gas, choking the very activity that sustains it. Too little inflow, and the fire slowly dies. The galaxy walks a tightrope, a delicate balance between gravity and pressure, inflow and outflow, creation and destruction. It is precisely this balance that makes NGC 2903 such a rich subject for study. Its core is not only a site of rapid evolution, it is a snapshot of galaxy transformation in action. While many galaxies undergo starbursts during cataclysmic events like collisions or interactions, NGC 2903 shows us that such fireworks can emerge from within. Its bar channels the raw materials, its gravity fuels the compression, and its stars carry out the cycle, over and over again. Here, in the heart of a relatively unassuming galaxy in Leo, lies a crucible of change. It is easy to be mesmerized by the swirling arms or the grandeur of the whole, but the real story is in the center, where stars are born faster than the eye can track, and where every particle of gas is locked in a race against time. This is the essence of the starburst core, a localized, high-efficiency engine of cosmic creation, sculpted not by chaos, but by structure, a flame hidden in the lion's chest, roaring quietly across millions of light years. The heart of NGC 2903 glows with a silent fury, but much of its story remains veiled behind clouds of cosmic dust, obscured from the visible spectrum and shielded from traditional optical telescopes. To the naked eye, or even through powerful optical instruments, the galaxy's central starburst appears only as a concentrated region of brightness. The chaotic brilliance, the sculpting winds, the tangled webs of gas and dust, these remain shrouded. But when astronomers shift their gaze to the infrared, the galaxy transforms. What was once hidden becomes incandescent. The galaxy speaks in heat, and in that language, its secrets emerge. Infrared astronomy has revolutionized our understanding of galaxies like NGC 2903. Because dust absorbs visible light but remits energy in the infrared, these longer wavelengths can pierce through the dust and reveal what lies behind it, especially the warm regions of gas and dust being heated by newly formed stars. Where optical observations give us structure, spiral arms, bulges, bars, the infrared reveals the processes, especially those hidden behind thick veils of interstellar matter. In the case of NGC 2903, infrared images show a core blazing with activity, far more intense than what is seen in visible light. Surveys by missions such as Spitzer and Herschel, both of which specialize in infrared astronomy, have revealed a central region aglow with thermal radiation, where dense knots of star formation heat surrounding dust to hundreds of degrees Kelvin. These heated dust clouds, invisible in optical wavelengths, shine brightly in the mid and far infrared, like embers seen through the smoke of a dying fire. This glow is not uniform. It flickers in concentrated pockets, compact star-forming regions just a few hundred light-years wide. Some of these regions are so deeply embedded in dust that they remain invisible in all but the longest wavelengths. These infrared bright areas correspond to ultra-compact H2 regions, where young, massive stars ionize their surroundings while still enveloped in the dense gas clouds from which they were born. In some parts of NGC 2903's core, these clouds are so thick that even near-infrared light is partially absorbed, making far-infrared and submillimeter wavelengths critical for detecting their heat signatures. The temperature of this dust tells astronomers much about the environment. Colder dust, around 20 to 30 K, indicates more quiescent areas, perhaps places where gas is accumulating but not yet forming stars. Warmer dust, around 70 to 100 K or higher, signals active star-forming zones, heated by UV radiation from young stars and by the mechanical energy of stellar winds and supernovae. In NGC 2903, the core glows predominantly with this warmer dust, painting a thermal image of a galaxy in the act of transformation. Beyond just the core, infrared imaging also traces the bar structure more clearly than optical images can. The dust and gas channeled by the bar emit strongly in the mid-infrared, especially at wavelengths dominated by polycyclic aromatic hydrocarbons, PAHs, complex organic molecules that glow when excited by ultraviolet light. These emissions outline the dust lanes that run parallel to the bar, tracing the gravitational routes along which gas is funneled toward the core. It is in these narrow streams that raw material flows, feeding the engine of stellar birth and lighting up the path with warmth. Infrared observations also hint at the depth and density of the material in the core. High-resolution maps at multiple infrared wavelengths allow astronomers to model the dust mass and estimate how much gas must be present. In NGC 2903, this modeling suggests that the central region contains several million solar masses worth of cold molecular gas, tightly packed into a volume just a few hundred parsecs across. This material acts as both the fuel and the veil of the starburst, the stuff from which stars are born and the cloak that hides their formation. Perhaps most striking is how the infrared luminosity of NGC 2903 compares to other galaxies. While it's not as extreme as the most luminous infrared galaxies, those often triggered by galaxy mergers, it still ranks high among normal, spiral galaxies. The infrared output from the core of NGC 2903 alone rivals the total luminosity of entire small galaxies, a testament to the sheer scale and efficiency of its central engine. This glow is more than beautiful, it's diagnostic. The ratio of infrared to visible light offers insights into how obscured the star formation is. In many galaxies, visible light alone severely underestimates the true star formation rate, because much of it is hidden behind dust. In NGC 2903, the discrepancy is particularly pronounced in the nucleus, where dense dust clouds absorb up to 90% of the light emitted by young stars. Without infrared observations, this entire furnace would be underestimated, if not completely missed. Spectroscopy in the infrared adds another layer of understanding. By splitting the infrared light into its component wavelengths, astronomers can identify specific chemical signatures, tracers of warm dust, shocked gas, and ionized material. Observations of lines like the N2 emission at 12.8 microns, for example, provide insight into the number and energy of young, massive stars buried within the dust. In NGC 2903, these signatures confirm an intense rate of star formation and reveal a rich chemical environment, enriched by previous generations of stars and stirred by ongoing turbulence. This vibrant activity, however, is largely invisible in optical wavelengths. In visible light, the core of NGC 2903 appears bright, yes, but serene. Only with infrared eyes do we see the chaos beneath, the shock waves, the violent winds, the radiation streaming from embryonic stars, all of it hidden beneath a calm facade. The galaxy wears a mask in visible light. Infrared light strips that mask away. And perhaps most astonishingly, these observations don't just illuminate the present, they also peer into the galaxy's future. The reservoirs of cold dust and molecular gas seen in the far infrared and submillimeter suggest that the starburst in NGC 2903's core could continue for millions of years. Unlike explosive events triggered by collisions, which often burn bright and fade quickly, this is a self-sustaining, internally driven blaze. It doesn't flare, it smolders, controlled yet intense, like a furnace that never quite goes out. As technology continues to improve, especially with space telescopes like the James Webb Space Telescope, the resolution and sensitivity of infrared observations will deepen our view of NGC 2903 even further. Already, early images from JWST of other galaxies have revealed intricate structures of star formation and dust never before seen. It is only a matter of time before NGC 2903 is examined with such clarity, offering us a front-row seat to one of the universe's most productive star factories, hidden in plain sight behind a veil of dust. In a cosmos where light is often the only messenger, the shift from optical to infrared is not just a technical adjustment, it's a philosophical one. It reminds us that beauty, power, and transformation often lie hidden behind obscuring veils. And with NGC 2903, what we find beneath those veils is a blaze, not of destruction, but of creation, burning with the heat of a million suns yet to be born. The central region of NGC 2903 may shimmer with the warm, golden light of star formation, but beneath that radiant glow lies a cauldron of chaos. It is not just bright, it is violent. Behind the veil of infrared brilliance, the starburst core of this galaxy plays host to a symphony of turbulence, where the very act of creation triggers destruction, and every new star is born into a storm. Starburst regions, by their very nature, are extreme. They do not form stars gently or passively. They do so explosively, compressing gas under immense pressure, igniting massive stars at a staggering rate. And these massive stars, tens of times the mass of our Sun, live fast and die young. Within just a few million years of their birth, they end their lives as supernovae, unleashing blasts of energy that ripple through the surrounding interstellar medium like shockwaves from a bomb. In NGC 2903's core, where stars are forming at many times the rate seen in the Milky Way, these explosions occur frequently, one after another, echoing through the molecular clouds. Each supernova is more than just a death, it is a transformative event. The shockwaves from these explosions sweep up surrounding gas, heating it to millions of degrees, generating X-ray emitting plasma and carving out vast cavities in the interstellar medium. These hot bubbles expand, collide, and interact with other shock fronts, resulting in an environment of turbulence and feedback. What was once a quiet cloud of gas becomes a maelstrom of movement and heat. This feedback is essential. It regulates the rate of star formation, prevents runaway growth, and helps redistribute material throughout the galaxy. But it also injects the region with energy that makes it anything but calm. Observations from space telescopes like Chandra and XMM Newton in the X-ray band have detected diffuse, high-temperature gas in NGC 2903's central region, clear evidence of this ongoing violence. The temperatures in these bubbles can soar to several million Kelvin, far hotter than the surfaces of the stars that triggered them. These regions glow not with the warmth of starbirth, but with the raw heat of shock. They are cosmic pressure cookers, filled with energized particles moving at supersonic speeds. And it's not just localized bubbles. Collectively, the energy from hundreds or thousands of massive stars and supernovae gives rise to something even more dramatic: superwinds. These are powerful, galaxy-scale outflows of gas that stream away from the central region like steam from a volcanic vent. In NGC 2903, these winds carry gas vertically out of the galactic plane, creating what astronomers call a galactic fountain. Material is ejected from the core, only to cool and rain back down on the disk, potentially fueling future star formation. These winds are not theoretical. They've been detected in spectral observations. Using instruments that can resolve fine details in emission lines, astronomers have measured the Doppler shifts in light coming from gas in the central region. These shifts show gas moving at speeds of hundreds of kilometers per second, directed away from the galactic nucleus. The fingerprints of outflowing material, especially ionized gas like oxygen and nitrogen, reveal a dynamic system in which energy is constantly being transferred from stars to gas, and from the core to the galaxy at large. What's particularly striking about NGC 2903 is that all this is happening without any major external provocation. Unlike many violent starbursts triggered by galaxy collisions, like what we see in the antennae galaxies or M82, NGC 2903's turbulence is driven purely by internal dynamics. The bar channels gas inward, star formation ignites, massive stars explode, and the whole cycle feeds itself in a self-regulating loop of creation and chaos. This makes NGC 2903 a rare and invaluable laboratory, a secular starburst happening in isolation, driven by structure rather than interaction. This internal violence also sculpts the galaxy's appearance over time. The winds can shape the morphology of the central region, pushing gas into rings or arcs, disrupting smooth flows and replacing them with shock fronts. Dust lanes become twisted and irregular. The once smooth central bulge takes on a patchy, turbulent texture. Infrared images often show asymmetries and knots, indications of areas where winds and explosions have stirred the pot. The presence of superstar clusters in the core further amplifies the violence. These dense, gravitationally bound groups of young stars act like power plants. A single superstar cluster may contain tens of thousands of massive stars, each contributing winds and radiation pressure. The combined output of a single cluster can be enough to drive a small wind, but when multiple clusters are packed into a small volume, as they are in NGC 2903's nucleus, the result is a collective outflow, a coordinated storm that pushes gas outward with relentless force. This process doesn't just affect the galaxy, it enriches the circumgalactic medium. As winds push material out into the space surrounding the galaxy, they carry with them heavy elements, carbon, oxygen, silicon, created in the cores of dying stars. These metals seed the surrounding environment, helping to fertilize future generations of stars and galaxies. In this way, the violence within NGC 2903's core contributes to the chemical evolution of the universe itself. But the winds also come at a cost. If too much gas is expelled too quickly, the galaxy may eventually quench its own starburst. The delicate balance between inflow and outflow must be maintained. Some of the gas pushed outward by winds cools, slows down, and falls back, recycled into the next generation. But some escapes entirely, drifting into intergalactic space, lost to the galaxy forever. This delicate interplay, between creation and destruction, between the bright glow of young stars and the violent winds they unleash, is what defines NGC 2903's core. It is not a calm nursery of stars. It is a forge, a battlefield, a storm-racked region where gravity, pressure, heat, and motion collide in a spectacle of cosmic energy. And yet, this violence is not chaotic, it is organized. It emerges from structure, from the deliberate geometry of the bar, from the laws of physics acting over vast scales. What looks like disorder is, in truth, a finely tuned system of feedback and equilibrium. The core burns, not out of panic, but with purpose. And through that fire, the galaxy continues to evolve, one explosion at a time. NGC 2903 may lie over 30 million light-years away, but when astronomers look at it, they see a reflection, something strikingly familiar, like a distant cousin of our own Milky Way. In many ways, the two galaxies share a common blueprint. Both are barred spiral galaxies, both are rich in stars and gas, both possess majestic spiral arms that wind outward from a central hub. They are roughly similar in size, composition, and structure. But beyond these surface-level similarities, there lies a profound difference. NGC 2903 is simply more alive at its center. Let's begin with the basics. The Milky Way is classified as a barred spiral galaxy, just like NGC 2903, with a designation somewhere between SBBC and SBC, depending on which structural studies you consult. It has a central bar stretching across several thousand light-years, spiral arms filled with star-forming regions, and a halo of older stars and globular clusters. Its diameter is estimated at about 100,000 to 120,000 light-years, with a stellar population numbering in the hundreds of billions. NGC 2903, for its part, has a diameter close to 80,000 to 100,000 light-years, making it comparable in scale. It, too, is thought to harbor hundreds of billions of stars, possibly approaching a similar stellar mass. When comparing them side by side, one might imagine that NGC 2903 is simply another version of the Milky Way, an extragalactic mirror. But it is at the galactic core, where similarities give way to contrast. While the Milky Way's center is relatively subdued, home to a modest star formation rate and a mostly quiet supermassive black hole, NGC 2903's core is blazing with activity. Its central starburst region is forming stars at a far higher rate, its bar is channeling gas more efficiently, and its nucleus is far more turbulent and energized. The star formation rate in the Milky Way hovers around 1 to 2 solar masses per year, distributed across the disk and concentrated in regions like the Orion Arm. NGC 2903, on the other hand, is forming stars at multiple times that rate, and much of that activity is focused in the nucleus. In fact, its nuclear starburst is producing stars at a rate that might be 5 to 10 times higher than the Milky Way's average, depending on how you define the central region. This makes NGC 2903 not just active, but intensely efficient. Why this difference in activity? It comes down largely to internal dynamics. In NGC 2903, the central bar appears to be highly efficient at funneling gas inward toward the galactic center. The gas doesn't just swirl aimlessly, it is channeled along narrow dust lanes that extend from the spiral arms, along the bar, and into the core. The Milky Way also has a bar, but its gas inflow appears to be more moderate. Whether due to differences in bar strength, gas availability, or central mass distribution, the Milky Way's bar is less of a fire hose and more of a trickle compared to NGC 2903's. Additionally, the central molecular zone in NGC 2903 is more massive and dense. Observations of molecular gas, using carbon monoxide and other tracers, show that the inner kiloparsecs of NGC 2903 hold hundreds of millions of solar masses worth of star-forming material, tightly packed into a disk where conditions are just right for triggering new stars. The Milky Way's core has molecular gas too, but it's distributed differently, and much of it may be more diffuse or tied up in long-lived clouds that don't collapse as readily. In NGC 2903, the gas collapses faster, forms stars quicker, and in turn creates more feedback that stirs the cycle anew. There's also the matter of feedback regulation. In the Milky Way, star formation in the center may be suppressed in part by feedback from the central black hole, Sagittarius A. Though currently quiescent, SGRA may have been more active in the past, possibly producing jets or outflows that cleared gas from the core. NGC 2903, while likely also hosting a central black hole, shows no signs of an active galactic nucleus, AGN. Its black hole is either small, underfed, or dormant. Without strong AGN feedback, more gas remains available to fuel the starburst. In other words, the very engine that might quench a galaxy's core in one case may be silent in the other, allowing the starburst to proceed unhindered. And yet, the comparison is instructive. It shows us what the Milky Way could have looked like, and perhaps once did. Some simulations suggest that galaxies go through phases of increased central activity, driven by bar evolution, gas accretion, or even minor mergers. It's possible that the Milky Way, too, experienced a central starburst billions of years ago and has since settled into a more passive state. NGC 2903, by contrast, may be in the middle of its fiery phase, caught in the act of transformation. On a structural level, both galaxies show complex spiral patterns with well-defined arms, although NGC 2903's arms appear more symmetric and smoother, suggesting a quieter history with fewer disruptive interactions. The Milky Way has endured a series of minor mergers, most recently with the Sagittarius dwarf galaxy, that have distorted its arms and thickened its disk. NGC 2903 seems more isolated, evolving mostly under its own gravitational influence. And yet this isolation has not led to passivity. It has instead allowed internal structures like the bar and spiral density waves to flourish, free from external interference. In terms of mass distribution, both galaxies host significant dark matter halos, as inferred from their flat rotation curves. This similarity points to a shared evolutionary lineage in the broader sense. The stars and gas we see are only the tip of the iceberg. Both galaxies are embedded in much larger halos of invisible mass that shape their dynamics, growth, and interactions with the cosmic web. Ultimately, the comparison between NGC 2903 and the Milky Way is a study in parallels and divergence. They share a morphology, a scale, and a structure, but their central lives tell different stories. NGC 2903 is a vision of what a galaxy like ours might become, or might once have been, if its internal machinery were tuned just slightly differently. Its active, glowing heart contrasts sharply with our own relatively subdued core, reminding us that galaxies are not static entities but evolving, breathing systems. Their brightness, their violence, their quiescence, all are chapters in a much longer story written in stars. In the grand design of the cosmos, spiral galaxies are some of the most mesmerizing, majestic pinwheels of stars spinning gracefully through space. But a substantial number of them, including both NGC 2903 and our own Milky Way, belong to a special class known as barred spiral galaxies. These galaxies contain a striking linear structure, an elongated bar of stars, running through the center, connecting the inner nucleus to the spiral arms. This bar is not just a visual flourish, it is a powerful dynamical feature, a mechanism that fundamentally transforms how matter moves within a galaxy. In barred spirals like NGC 2903, this structure is the key to unlocking and fueling the central starburst activity. At first glance, a bar might seem like a static formation, simply an arrangement of stars orbiting in an elongated path. But its impact on a galaxy's evolution is profound. The bar acts as a gravitational engine, stirring the pot of the galactic disk and redistributing matter in a way that spiral arms alone cannot. It's not an ornament, it's a conveyor belt, constantly working behind the scenes to shape the galaxy's future. The process begins with the bar's ability to torque the gas within the galactic disk. In a non-barred spiral galaxy, gas typically orbits in nearly circular paths around the center, slowly drifting inward or outward depending on local gravitational influences. But in a barred galaxy, the bar creates a non-axisymmetric gravitational potential, a sort of gravitational asymmetry that disrupts these circular motions. Gas clouds feel a continual tug from the bar, especially as they pass near its ends. This gravitational nudge causes gas to lose angular momentum, which is just a fancy way of saying it loses some of its tendency to spin and begins to fall inward. This inward flow is not random. It follows very specific routes along the bar, often visible as dust lanes in high-resolution images. These lanes trace the path of cold gas and dust as it streams toward the core, compressed and shaped by the gravitational forces at play. Along the way, the gas experiences shocks, heating up slightly, becoming denser, and forming massive molecular clouds. These clouds, in turn, are prime breeding grounds for star formation. But the bar doesn't just deliver the gas. It also organizes it. Through a process known as resonance trapping, the bar induces zones within the galaxy where the motion of gas and stars becomes synchronized with the bar's rotation. The most famous of these is the inner Lindblad resonance, ILR, a region near the center of the galaxy where inflowing gas can become trapped in a stable ring-like orbit. These rings often mark the location of nuclear star-forming rings, compact, circular regions where gas accumulates and is converted rapidly into new stars. In NGC 2903, such a ring is believed to exist, blazing with the heat and energy of intense starburst activity. The beauty of this mechanism is its efficiency. Rather than relying on external events, like galaxy mergers or tidal disruptions, to drive gas into the core, barred galaxies have their own built-in funnel. The bar takes the vast, diffuse gas of the outer disk and steadily channels it inward. In doing so, it feeds the central engine, whether that's a starburst, a central black hole, or both. In many galaxies, this process leads to a transformation of the galactic core. The constant supply of fresh gas fuels rejuvenated star formation, making the nucleus significantly younger than the rest of the galaxy. Over time, the influx of stars increases the mass and brightness of the bulge, changing the overall appearance of the galaxy. Some models even suggest that bars can trigger or grow central supermassive black holes by delivering dense material into their gravitational grasp. Although NGC 2903 shows no signs of a currently active black hole, the potential for such a process remains. Interestingly, bars are also self-limiting. As they transfer angular momentum outward and mass inward, they can become stronger, elongating and thickening with time. But eventually, if too much mass accumulates in the core, the gravitational dynamics can change enough to weaken or even dissolve the bar. In this way, the bar's life is tied intimately to the activity it triggers. It is both the catalyst and, potentially, its own undoing. Computer simulations of galaxy evolution vividly illustrate this process. When a spiral galaxy with a bar is modeled over billions of years, one can watch as gas is drawn inward, forms stars, and then interacts with the feedback from those stars, winds, radiation, and supernovae. The central bulge grows, the star formation rate spikes, and the spiral structure evolves. These simulations confirm what astronomers observe in galaxies like NGC 2903. The bar is the primary driver of secular evolution, reshaping the galaxy from within, without any need for external collisions. NGC 2903 is a textbook example. Its bar is well developed and clearly visible in near-infrared and optical images. Its dust lanes trace gas inflow paths that lead directly into the starbursting core. Spectroscopic studies show rotation patterns consistent with bar-driven dynamics. And perhaps most convincingly, it exhibits all the signs of a bar-fueled central furnace, a nucleus dense with gas, rich in young stars, and alive with turbulence. So while it may look like a simple bright stripe across the galaxy's middle, the bar is anything but passive. It is a sculptor of galaxies, a conveyor of change, and the trigger for some of the universe's most beautiful violence. Through its influence, galaxies like NGC 2903 light up their hearts, not in random flashes, but in rhythms dictated by gravity, structure, and time. To understand what truly fuels the fury at the core of NGC 2903, we have to trace the journey of something deceptively simple: cold interstellar gas. It is this gas, silent, invisible, and ancient, that lies at the heart of the galaxy's transformation. And while its journey begins in the outer reaches of the galactic disk, it ends in the white-hot crucible of the nucleus, where stars are born by the thousands in the midst of violent energy exchanges. The question, then, is how this quiet, diffuse material becomes the engine of a raging starburst. The answer lies in the bar, gravity, pressure, and the delicate dance of galactic dynamics. In the outer disk of NGC 2903, gas exists in two major forms: atomic hydrogen, Hi, which is relatively diffuse, and molecular hydrogen, H2, which is colder and clumps into clouds. This gas is scattered throughout the spiral arms, often concentrated in dust lanes that follow the patterns of density waves, those gently rotating ripples that sweep through spiral galaxies and gather gas into long arcs. In isolation, these clouds might slowly evolve, collapse under gravity, and form stars at a leisurely rate. But in NGC 2903, that leisurely process is overridden by the influence of its bar structure. The bar acts as a channel of gravity, reshaping the orbit of stars and gas alike. As the bar rotates, and it does so at a different speed from the spiral arms, it sets up a gravitational asymmetry that affects how gas flows. Gas clouds feel a continuous inward pull, especially along the bar's leading edges. But unlike stars, which can follow elongated orbits under the influence of the bar, gas behaves like a fluid. It shocks, compresses, heats, and cools. This difference is critical. As clouds approach the bar's length, they collide with one another, compress, and lose angular momentum. This loss causes them to drift inward along the bar, almost like water running down a chute. These inflow lanes are visible in many barred galaxies, including NGC 2903, as straight dust lanes along the bar, offset slightly from the bar's center. Observations in infrared and optical bands show that these dust lanes are thick with cold material, traced by CO emissions and other molecular signatures, moving inward toward the galaxy's nucleus. As this gas piles up, it begins to form massive molecular clouds, rich in the raw ingredients for star formation: hydrogen molecules, helium, carbon compounds, and dust particles. But it's not just the bar that's compressing this gas. As it flows inward, the gas encounters resonant zones, regions of the galaxy where the orbital motion of the gas lines up with the gravitational frequencies induced by the bar's rotation. The most significant of these is the inner Lindblad resonance, ILR. At this location, inflowing gas tends to accumulate, forming dense rings or disks of molecular material. In NGC 2903, such a ring has been detected just a few hundred parsecs from the center, brimming with compact star-forming regions and glowing in infrared. In these rings, gas densities skyrocket. The clouds become gravitationally unstable, begin to fragment, and collapse under their own mass. This is where star formation ignites, rapidly and in bursts. Clusters of massive stars begin to form in tightly packed groups, lighting up the region and sending out winds that stir the environment even further. But the key lies in the compression itself. Without the bar and its resonant inflow, this level of compression might never occur. The physics of this transformation are breathtakingly complex. As gas flows inward along the bar, it experiences shock fronts, where it is violently compressed and heated before cooling again. These shocks can occur where the bar transitions into the nuclear ring, or at points where gas streams converge. Turbulent flows form within the clouds, driving instabilities that seed fragmentation. Some clouds experience shear, forces that stretch and twist them, while others are compressed from multiple sides. The end result is a chaotic, high-pressure environment where gravity takes over and collapses the densest regions into protostellar cores. Once stars begin to form, they immediately begin influencing the next generation. Massive stars shine with ultraviolet light, ionizing nearby hydrogen gas and forming H2 regions, glowing bubbles of plasma that act like beacons in the galactic night. Their stellar winds carve cavities in the molecular clouds, compressing gas in some areas while dispersing it in others. When these stars die as supernovae, the resulting shock waves ripple outward, further compressing surrounding material and triggering yet another round of star formation. This is known as positive feedback, and it can drive cycles of starburst that propagate through the central region in waves. NGC 2903's ability to maintain this process is partly due to its abundant reservoirs of neutral and molecular gas. Observations show that it possesses a large halo of atomic hydrogen, extending well beyond the visible disk. This halo serves as a kind of gas bank, potentially supplying the galaxy with fresh material that can be drawn inward over time. Through a slow but persistent mechanism known as galactic accretion, this gas can fall into the disk, be converted into molecular form, and then flow inward along the bar. It's a long game, one that may continue feeding the starburst for tens to hundreds of millions of years. Radio observations using facilities like the Very Large Array, VLA, and ALMA have mapped the distribution and motion of gas in exquisite detail. These maps show the characteristic signs of inflow, non-circular motion patterns, velocity gradients along the bar, and enhanced gas densities near the center. In CO maps, the molecular gas lights up like veins of fuel converging on the galactic furnace. NGC 2903 is not just forming stars, it's drawing in the material to do so, like a cosmic engine pulling fuel from distant tanks. One of the most fascinating aspects of this inflow mechanism is how it maintains balance. The rate at which gas is drawn inward must match, or nearly match, the rate at which it is consumed or blown out by feedback. If gas flows in too quickly, it can oversaturate the core, triggering overly violent outbursts or exhausting the galaxy's reserves too soon. If it flows in too slowly, the starburst will sputter and fade. But in NGC 2903, the balance seems just right. The inflow is steady, the gas dense, the feedback fierce but not overwhelming. It is a system in equilibrium, tuned over millions of years. And it is beautiful in its design. The galaxy does not need a collision, a merger, or an outside provocation. The fuel is there, the path is clear, the engine is running. The bar pulls in the gas, compresses it, and lights it on fire, celestially speaking. Each cloud that collapses, each star that ignites, each supernova that detonates, all of it traces back to this simple, elegant mechanism, gravity pulling gas along the bar. In the end, what feeds the starburst in NGC 2903 is not chaos but structure. It is the galaxy's own architecture that drives the storm. Through the bar's influence, cold gas becomes compressed, fragmented, ignited, and transformed. What begins as a whisper in the outer disk becomes a roar at the center, a blaze born of dust and pressure, powered by the steady inward march of matter. Among the many marvels hidden within the heart of NGC 2903, few are as luminous, or as telling, as the superstar clusters that dot its central starburst region. These are not ordinary groups of stars. They are dense, massive, and short-lived crucibles of stellar birth, places where stars don't form one at a time, but by the thousands in a single cosmic breath. To peer into these clusters is to witness the galaxy at its most creative, most furious, and most alive. Superstar clusters, SSCs, are, by definition, tightly packed groups of very young, massive stars, often less than a few million years old. Unlike open clusters, which typically contain a few hundred stars and are loosely bound, SSCs can contain tens of thousands to even millions of stars packed into volumes only a few light-years across. They are miniature versions of globular clusters, though far younger, and many astronomers suspect that some SSCs may, over billions of years, evolve into globular clusters themselves. In NGC 2903, the presence of these superstar clusters is clear and compelling. High-resolution imaging in infrared, optical, and radio wavelengths has revealed multiple compact, brilliant sources embedded in the central kiloparsec of the galaxy. These sources emit intense ultraviolet and ionizing radiation, flood their surroundings with stellar winds, and are often partially obscured by dense clouds of gas and dust. These are the signature traits of SSCs, newborn stellar cities, barely emerged from the cocoons that formed them. The clusters in NGC 2903's central region are especially interesting because they coexist in the thick of the starburst zone, where gas densities are highest, pressures are extreme, and feedback is intense. These conditions are ripe for the formation of massive clusters. In less active parts of a galaxy, gas clouds may fragment and form stars over longer periods, resulting in loose associations. But in the core of NGC 2903, gas is compressed violently, triggering rapid, large-scale collapse. The result? Gigantic clouds that form not one star, but thousands, nearly simultaneously. These clusters often begin their lives as embedded sources, still cloaked in the dense dust and gas that birthed them. In visible light, they are nearly invisible. But in the infrared, they shine like coals behind a curtain of smoke. Instruments aboard the Spitzer Space Telescope and, more recently, the James Webb Space Telescope have revealed these glowing cores, some less than 5 light-years in diameter, yet outshining entire regions of the galaxy. Their brightness is not only due to the number of stars, but also their youth. Most SSCs are populated with O-type and B-type stars, the most massive and luminous types in the stellar family. These stars burn hot, live fast, and die young, making the clusters both radiant and temporary. The environments around these clusters are equally dynamic. The ultraviolet radiation from young, hot stars ionizes the surrounding hydrogen, creating H2 regions that glow in the optical and infrared. These ionized zones expand outward, sometimes merging with the ionized bubbles of neighboring clusters, creating a patchwork of plasma around the galactic center. Meanwhile, stellar winds from the most massive stars, moving at speeds of thousands of kilometers per second, begin to sculpt cavities in the surrounding gas, compressing some regions and dispersing others. These feedback effects have a double-edged nature. On one hand, they help regulate star formation, preventing runaway collapse by heating and dispersing gas. On the other hand, the shocks from these winds can compress other parts of the cloud, triggering new clusters to form nearby. In this way, SSCs in NGC 2903 may be triggering successive generations of star formation, cascading outward like ripples in a pond. Spectroscopic studies of these clusters add another layer to the story. By splitting their light into component wavelengths, astronomers can detect emission lines from ionized elements like oxygen, nitrogen, and sulfur. These lines reveal both the physical conditions inside the clusters and the metallicity of the stars, telling us whether the gas they formed from was rich or poor in heavy elements. NGC 2903's SSCs show signs of moderately enriched material, suggesting that previous generations of stars had already seeded the region with metals before these clusters formed. The dynamics within the clusters are also extreme. The density of stars is so high that gravitational interactions become significant, stars can deflect one another, binaries can be disrupted, and mass segregation can occur very early. In fact, some theories suggest that in the densest clusters, runaway stellar collisions could lead to the formation of extremely massive stars or even intermediate mass black holes, though this remains speculative. And yet, despite their violence, these clusters are remarkably coherent structures. Many remain gravitationally bound for tens of millions of years, resisting dispersal even as some of their most massive stars explode as supernovae, flooding their interiors with energy and ejecta. These supernovae add another layer of feedback, injecting energy into the surrounding medium, enriching it with heavy elements, and contributing to the winds that flow outward from the galactic center. NGC 2903 doesn't host just one or two SSCs. It likely hosts dozens, possibly more, arranged in a loose complex that fills the nuclear starburst zone. Observations have detected clusters in various stages of development, from deeply embedded protoclusters barely visible even in infrared, to more evolved systems where dust has cleared and the full population of stars can be studied directly. This diversity of ages offers a snapshot of cluster evolution, all contained within a single, glowing heart of a galaxy. And it raises fascinating questions about the fate of these clusters. Some may dissolve over the next 100 million years, their stars dispersing into the galaxy's bulge and disk. Others may survive intact, gradually evolving into compact, long-lived globular clusters, the kinds we see orbiting the halos of many galaxies today. If so, then the globular clusters that surround the Milky Way may be the fossil remnants of ancient starbursts, not unlike what we see happening in NGC 2903 right now. In the end, these superstar clusters are more than just brilliant fireworks in a distant galaxy. They are the building blocks of galactic evolution, the high-energy laboratories where the universe refines its processes of creation. They tell us how stars form in extreme environments, how feedback shapes the interstellar medium, and how galaxies regulate their own growth. And in the case of NGC 2903, they remind us that even in solitude, a galaxy can burn with the intensity of 1,000 suns, not through external violence, but through the intricate interplay of structure, gas, gravity, and time. The heart of NGC 2903 is not just a glowing forge of newborn stars, it's a launch pad. A place where the act of creation is so intense, so concentrated, that it sends matter streaming out into the galaxy and beyond. These streams, known as galactic winds, are one of the clearest signatures that a galaxy is undergoing more than just normal star formation. They're a sign of transformation. And in NGC 2903, those winds are real, observable, and shaping the galaxy's future even as they trace the violent consequences of its present. Galactic winds arise when the energy released by massive stars, supernovae, and star-forming clusters exceeds the gravitational pull of the surrounding region. In less intense galaxies, such outflows are mild or non-existent. But in starburst galaxies like NGC 2903, where massive stars are being formed rapidly and supernovae are detonating frequently, the energy output is immense. Thousands of young stars emit stellar winds, high-speed outflows of gas ejected from their surfaces. And when those stars die, their deaths send shockwaves rocketing through the interstellar medium. This collective energy pushes gas outward, heating it, ionizing it, and in some cases accelerating it to escape velocities. In NGC 2903, signs of these outflows come from multi-wavelength observations, each revealing a different layer of the process. At optical wavelengths, narrowband imaging around specific emission lines, such as H-alpha, N2, and O3, shows bubble-like structures near the central starburst zone. These bubbles are telltale signs of gas being pushed outward by internal pressure. In some regions, these bubbles appear to open up into chimneys or funnels, where hot gas escapes vertically out of the galactic plane. Infrared and X-ray observations add more pieces to the puzzle. Instruments like Chandra and XMM Newton detect diffuse X-ray emission in and above the galactic center of NGC 2903. This emission comes from gas that's been heated to millions of degrees, a clear sign that it has been shock-heated, likely by overlapping supernova remnants. These hot regions don't just linger, they move. Spectroscopic data taken from ground-based observatories and space telescopes reveals that the emission lines from ionized gas in the central region are often asymmetric or broadened, suggesting gas is not just sitting still, but streaming outward at high velocities. One of the strongest pieces of evidence comes from the Doppler shift in emission lines. By measuring how these lines are shifted toward the red or blue end of the spectrum, astronomers can detect motion toward or away from Earth. In NGC 2903, these shifts show that some of the gas in the nucleus is moving outward at hundreds of kilometers per second, especially perpendicular to the disk, classic behavior for bipolar outflows. These winds often escape through the path of least resistance, straight up and down from the galactic plane, where there is less interstellar material to block them. But these outflows are not smooth, singular jets. They're turbulent, clumpy, and stratified. Observations show that different gas phases, cold molecular gas, warm ionized gas, and hot X-ray emitting plasma, are being ejected together, but not at the same rates or speeds. The hottest gas travels fastest and farthest, while denser material lags behind. This creates a layered wind structure, with the core composed of high-speed plasma and the outer shell made of slower, cooler clouds. In some galaxies, these winds are strong enough to expel significant amounts of gas entirely out of the galaxy, contributing to a phenomenon known as quenching, where star formation slows or stops because the fuel has been blown away. In NGC 2903, the winds appear to be powerful but not yet catastrophic. There is still plenty of gas in the nucleus, and the galaxy continues to birth stars at an accelerated rate. But the winds are sculpting the region, perhaps regulating the starburst, and ensuring that it doesn't burn through its resources too quickly. Moreover, these winds may serve a larger cosmic function. As they escape into the halo surrounding NGC 2903, they carry with them metals, the heavy elements created in stellar cores and supernovae. These metals enrich the circumgalactic medium, CGM, and over even longer timescales, the intergalactic medium, IGM. They play a crucial role in the chemical evolution of the universe, seeding future generations of stars and galaxies with the ingredients needed for planets and life. Without galactic winds, the cosmos would be a more primitive place, slower to evolve and less diverse in its structures. Interestingly, the orientation and structure of the outflows in NGC 2903 suggests that its winds are not caused by galaxy interactions. In galaxies like M82, dramatic winds are often the result of violent collisions or tidal forces. But NGC 2903 is an isolated galaxy. Its activity is driven internally, through the sustained, self-regulated starburst at its center. That makes its winds particularly valuable to astronomers, as they represent pure examples of feedback-driven outflows, unclouded by the complexity of mergers or accretion events. There are also subtle clues that these winds may be feeding a galactic fountain, a cycle in which some of the ejected gas cools and eventually falls back onto the galaxy's disk. This returning material can trigger secondary waves of star formation, especially in the outer regions or along the spiral arms. The idea of such a fountain aligns with observations that suggest some of the extraplanar gas in NGC 2903 is not fully escaping, but instead moving in long, arcing trajectories that bring it back into the gravitational fold of the galaxy. It's a cosmic recycling program, matter flung outward in a burst, only to return later as the seeds of new stars. All of this points to a galaxy that is not just forming stars, it is breathing. With every cycle of star formation, supernova, and wind, NGC 2903 exhales energy and matter into its surroundings. And over time, this breathing shapes the galaxy's structure, regulates its star formation, and enriches the space around it. In the grand scheme, galactic winds are part of the story of balance. Without them, galaxies might overfeed on their own gas, collapse into chaotic cores, or burn out prematurely. With them, galaxies can modulate their growth, pace their evolution, and sustain themselves across cosmic epochs. And in the brilliant, windswept nucleus of NGC 2903, we see that balance playing out in real time, a living laboratory of astrophysical feedback, driven not by violence alone, but by the structured breath of a galaxy alive with stars. NGC 2903 may present itself to the human eye, or the optical telescope, as a radiant whirlpool of stars, but that visible beauty is only one layer of a much deeper story. To truly understand this galaxy, astronomers have had to go beyond the visible spectrum, peeling back its outer glow using the full array of the electromagnetic spectrum. Each wavelength tells a different version of the same tale, one of gas and gravity, of structure and energy, of formation and feedback. In the case of NGC 2903, these multi-wavelength views are not just complementary, they are essential. They reveal different actors in the galactic drama: stars, dust, gas, winds, and together they construct a three-dimensional, time-sensitive portrait of a galaxy mid-evolution. Starting with optical light, the range our eyes can see, NGC 2903 appears as a stunning barred spiral galaxy with a golden center and bluish spiral arms. Optical telescopes capture the light emitted primarily by stars, especially young, hot stars that shine in blue and ultraviolet, and older, cooler stars that glow red and yellow. When we look at NGC 2903 in this light, the bar is clearly defined, stretching across the galaxy's center. The spiral arms are traced by bluish knots, regions of active star formation filled with young, massive stars. Bright patches of glowing hydrogen, H2 regions, dot the spiral arms, standing out in H-alpha filters, signaling where stellar birth is occurring. But optical light, for all its clarity, can't tell us everything. Much of the gas and dust within the galaxy absorbs or scatters visible light, obscuring our view of the core and other dense regions. That's where infrared observations become invaluable. Infrared light pierces through the dust that veils many of the galaxy's most dynamic zones. Observatories like the Spitzer Space Telescope and, more recently, the James Webb Space Telescope have shown us NGC 2903's hidden inner workings. In the infrared, the central bar becomes not just visible but vivid, glowing brightly due to warm dust heated by intense star formation. This infrared blaze in the nucleus reveals the galaxy's hidden furnace, the starburst core, where stars are being born at a furious rate. Dust, which absorbs optical light, re-radiates that energy in the infrared. Thus, regions that seem dark or muted in visible images suddenly shine with brilliance in the infrared, indicating the presence of embedded star-forming regions. These images also expose a more continuous dust lane structure, tracing the flow of interstellar gas from the spiral arms into the bar and ultimately into the galactic core. Where the optical view sees light and stars, the infrared view sees heat and structure, the skeleton of the galaxy's star-forming machinery. Moving even further along the spectrum, radio observations paint a different picture yet again, one dominated not by stars or dust, but by gas, particularly neutral hydrogen, Hi, and molecular gas traced by CO emissions. Using radio telescopes like the Very Large Array, VLA, or ALMA, astronomers have mapped the extended arms and halo of NGC 2903 in gas, revealing structures that stretch well beyond what's seen in optical or infrared. The neutral hydrogen extends into a vast halo, diffuse and invisible in optical light, that could serve as a long-term fuel source for future star formation. In these views, the spiral structure is more diffuse but more expansive, a kind of gaseous blueprint of the galaxy's future potential. Radio maps also show the detailed structure of molecular clouds within the galaxy. These are the nurseries of star formation, dense, cold regions where gravity can collapse gas into protostars. CO emission reveals concentrations of molecular hydrogen in the bar, in the nucleus, and along the spiral arms. By measuring the velocity of the gas via Doppler shifts, astronomers can track its motion, confirming inflow patterns along the bar, rotational speeds, and even the effects of feedback from young stars and supernovae. Beyond that, X-ray and ultraviolet wavelengths reveal additional layers. In X-ray, observed by telescopes like Chandra, we see supernova remnants and hot gas in the galaxy's core, evidence of intense stellar feedback and outflows. These X-rays originate from gas heated to millions of degrees by supernova explosions and stellar winds. The X-ray view shows that the starburst in NGC 2903 is not gentle, it's eruptive. Gas doesn't just collapse into stars, it also explodes outward, creating bubbles of million-degree plasma that glow in high-energy light. Meanwhile, in ultraviolet, we see the most massive and youngest stars, those that shine most brightly in the far UV. Telescopes like Galactic have imaged NGC 2903 in ultraviolet bands, highlighting clusters that are often missed in optical images due to their extreme youth or obscuration. These observations confirm the presence of superstar clusters, blazing with youthful intensity and flooding the galaxy with ionizing radiation. Combining all of these views, optical, infrared, radio, X-ray, ultraviolet, astronomers assemble a composite understanding of NGC 2903. The optical view shows the stars that already exist, the infrared shows us where stars are forming behind the dust, the radio reveals the gas yet to be turned into stars, the X-ray unveils the violence that comes from stellar death, and the ultraviolet shows us the stars just born. Each wavelength reveals a different phase of the galactic life cycle. This multi-wavelength approach doesn't just offer aesthetic diversity, it fundamentally changes how we understand the galaxy. For example, without infrared and radio data, astronomers might severely underestimate the star formation rate, since so much of the activity is hidden by dust. Without X-rays, they might miss the energetic feedback mechanisms that regulate that star formation. Without radio, they would miss the raw material, the fuel, that makes any of it possible. What makes NGC 2903 particularly exciting is how coherently these different layers align. It's not a chaotic mess of disconnected phenomena. It's a tightly knit system where every wavelength confirms and expands upon the others. The bar seen in optical and infrared is the same structure that guides gas inflow in radio. The infrared glow of young stars correlates with X-ray hot spots from their supernovae. The cold gas traced by radio CO lines is often found directly beneath the glowing dust cloud seen in Spitzer or JWST imagery. It's a galaxy in which structure, function, and feedback are deeply interwoven. And perhaps most beautifully, these views reveal that NGC 2903 is not merely active, it is layered with stories. It is forming stars not just because it has gas, or because it has structure, but because its entire body, dust, gas, gravity, heat, and pressure, is coordinated in motion. It is, in every sense, a galaxy at work. While the bright spiral arms and glowing core of NGC 2903 may command attention, much of the galaxy's long-term story is written in something far less visible, neutral hydrogen, or HI. This form of cold, unionized gas doesn't shine in optical light and doesn't glow in infrared, but it whispers across the cosmos in a specific 21-centimeter radio emission line. And when astronomers tune into that whisper, what they find surrounding NGC 2903 is a vast, invisible ocean, a halo of neutral hydrogen that stretches far beyond the luminous disk of the galaxy. It is both a relic of the past and a promise for the future, a massive reservoir of fuel that could one day ignite new waves of star formation, long after the current starburst has dimmed. Neutral hydrogen is the most basic and most abundant form of matter in the universe. In galaxies, it exists as a diffuse component of the interstellar medium, often forming the outermost layer of the galactic disk and the more extended halo. While molecular hydrogen, H2, is the immediate raw material for star formation, neutral hydrogen is its precursor, a cold, quiescent phase of gas that can cool, condense, and transform under the right conditions. In NGC 2903, the neutral hydrogen distribution provides deep insights into the galaxy's structure, evolution, and future potential. Radio observations, particularly those using the Very Large Array, VLA, and similar high-resolution interferometers, have mapped the HI content of NGC 2903 in impressive detail. These studies show that the galaxy's neutral hydrogen extends far beyond the optical disk, stretching to nearly twice the visible diameter of the spiral arms. While the bright parts of the galaxy span about 90,000 light-years across, the HI halo reaches out to over 200,000 light-years, forming a diffuse, asymmetrical cloud that envelopes the galaxy in a cold embrace. What's remarkable is how structured and dynamic this halo is. It's not just a uniform mist of gas. Instead, it contains clumps, filaments, and streamers, some of which appear to rotate along with the inner disk, while others follow more chaotic orbits. This hints at ongoing accretion, the process by which NGC 2903 is still gathering intergalactic material, slowly but steadily, feeding its star-forming regions with fresh gas. In this way, the galaxy is not an isolated island, but a living system exchanging matter with its cosmic surroundings. The presence of such a large HI halo also explains how NGC 2903 can sustain its central starburst for extended periods without the aid of galaxy collisions. In many other starburst galaxies, intense star formation is triggered by mergers or interactions that compress gas and feed the core. But NGC 2903's isolation makes its activity more unusual. Its gas is not being delivered by a companion. It's being pulled inward from its own extended reservoir, channeled through the bar, and ignited at the center. Some of this HI gas is slowly falling into the disk, either as part of a galactic fountain cycle, gas that was previously blown outward by winds and is now raining back down, or as fresh material from the intergalactic medium. This accretion helps maintain the galaxy's gas budget, offsetting what's lost to star formation, supernovae, and outflows. Without this supply, the central starburst would eventually exhaust itself. But with the HI halo in place, the galaxy has millions of years of fuel at its disposal. Moreover, studies of the kinematics of the neutral hydrogen, how it moves, how fast it rotates, reveal another important truth. The HI halo is a key probe of dark matter. The outer rotation curve of the galaxy, traced by HI gas far from the luminous stars, does not decline as Newtonian physics would predict. Instead, it remains flat, a classic signature of an unseen gravitational component. This means that the HI gas in the halo is not just passive fuel, it's a measuring stick for the galaxy's invisible mass, helping astronomers map the dark matter halo that envelopes NGC 2903. And yet, despite its size and importance, the HI halo is fragile. It is easily disturbed by gravitational interactions, cosmic radiation, or feedback from star formation. But NGC 2903's relative isolation seems to have preserved its HI reservoir well. There are no significant tidal tails or streams that suggest major past interactions. Instead, the gas appears coherent and stable, slowly feeding the disk, perhaps through cooling flows or infalling clouds that condense near the galaxy's outskirts. Interestingly, small-scale structures have been detected within the HI halo, compact high-velocity clouds that may represent the early stages of accretion or remnants of smaller, absorbed objects. These clouds are similar in nature to those seen around the Milky Way and other nearby galaxies, suggesting a common mechanism for halo gas dynamics across different environments. In NGC 2903, these clouds may play a role in maintaining, or even reigniting star formation in the spiral arms and core over cosmic timescales. In terms of mass, the HI content of NGC 2903 is substantial. Estimates suggest that it holds several billion solar masses worth of neutral hydrogen, comparable to or exceeding the molecular gas content in the central star-forming regions. This makes the HI halo not just a passive shell, but an active and vital component of the galaxy's ecosystem. It's like a great lung filled with breath, ready to be exhaled into new generations of stars. From a broader perspective, the neutral hydrogen halo of NGC 2903 serves as a reminder that galaxies are not closed systems. They live in constant dialogue with their environment, inhaling gas from the cosmic web, exhaling energy through feedback and winds, and gradually shaping themselves through cycles of loss and gain. In NGC 2903, we see this dialogue in action, not through dramatic collisions or explosive mergers, but through the quiet, persistent drift of cold hydrogen, flowing like an invisible tide. And it is this tide that promises to sustain the galaxy's brilliance. Long after the current wave of starburst clusters has faded, and long after the winds have blown their last breath, the HI halo will remain, waiting, drifting, slowly feeding the fire once again. When we peer into NGC 2903 through the lens of radio astronomy, we find ourselves listening to the coldest and quietest parts of the galaxy, the dark scaffolding on which its luminous structure is built. The stars that shine in optical and infrared may capture the eye, but it's the cold gas traced in radio wavelengths that reveals the fuel for the future, the shape of the past, and the hidden architecture guiding the galaxy's ongoing evolution. Through powerful radio telescopes like the Very Large Array, VLA, the Arecibo Observatory before its collapse, and other facilities such as the Atacama Large Millimeter/Submillimeter Array, ALMA, astronomers have mapped the unseen backbone of NGC 2903, and what they've discovered is as intricate as it is essential. Radio observations are uniquely suited to detect emissions from cold gas, particularly neutral atomic hydrogen, HI, and molecular gas like carbon monoxide, CO. These components are the raw materials from which stars are born, and their distribution tells us not only where stars might form in the future but also how gas flows through the galaxy and responds to gravitational forces. In NGC 2903, these radio maps reveal a galaxy shaped by a delicate and dynamic balance between its spiral arms, and extensive gaseous halo. One of the most striking features detected by the VLA and other arrays is the extended spiral structure traced by HI gas. While the optical spiral arms are already impressive, stretching nearly 90,000 light-years across, the radio observations show that the arms continue far beyond the visible disk. These ghostly spirals are fainter, less structured in appearance, but unmistakably present, curving well into the HI halo and hinting at a galactic influence that stretches over 200,000 light-years. This reveals that NGC 2903 is not just a galaxy of stars, but a vast, rotating reservoir of invisible matter, spinning and flowing quietly through space. The HI maps from the VLA, particularly those with high spatial resolution, also show velocity gradients along the spiral arms. These gradients tell astronomers how fast the gas is moving and whether it's following circular or elliptical orbits. In NGC 2903, the data shows a mostly ordered rotation, suggesting a stable disk, but with subtle twists and warps that hint at either internal dynamical processes or minor, past interactions. These distortions aren't violent, they're gentle, almost ghost-like, but they reveal that the HI gas is not simply static. It's breathing with the galaxy, shifting and adapting as gravity and feedback shape its motion. Zooming in toward the center of the galaxy, radio telescopes detect another key component, molecular gas, traced primarily by CO emissions. CO is not the most abundant molecule, that would be H2, but it's one of the easiest to detect at radio wavelengths and is used as a proxy for mapping dense molecular clouds. In NGC 2903, ALMA and similar arrays have detected concentrated bands of CO emission along the central bar and in the inner spiral arms, revealing the cold, compressed gas that is actively forming stars. The bar structure itself, so prominent in optical and infrared, is equally distinctive in CO radio maps. The molecular gas appears to flow along the bar, with denser clumps forming near the bar's ends and especially in the nuclear region. These inflow patterns align with the theoretical models of gas dynamics in barred galaxies. As gas moves inward under gravitational torques, it piles up at resonances, zones where orbital motions synchronize with the bar's rotation. In NGC 2903, radio data shows these convergences clearly, forming dense ridges that eventually fuel the central starburst. What's more, these same radio observations capture the outflows and feedback loops driven by stellar activity. In the central regions, CO maps show pockets of high-velocity gas moving away from the nucleus, evidence of galactic winds pushing against the inflow. This gives us a unique window into how NGC 2903 regulates its starburst. It pulls in gas to make stars, but also ejects gas through supernova-driven winds. The balance of these opposing flows, mapped in exquisite detail through radio line profiles, tells us how the galaxy sustains itself without burning out. Another major insight from radio studies is the distribution of dark matter, inferred through the analysis of rotation curves. By mapping the velocity of HI gas far from the center, well beyond the reach of most stars, astronomers find that the rotation speed doesn't drop off as expected. Instead, it remains remarkably flat, suggesting the presence of a massive, invisible halo of dark matter. In NGC 2903, this flat rotation curve confirms that much of the galaxy's gravitational mass lies outside its luminous components, and the radio data is the key tool for uncovering this dark skeleton. Even more subtle features emerge from deep radio surveys. Observers have found asymmetric structures. One side of the galaxy's HI distribution appears slightly more extended than the other. This could point to mild accretion events, perhaps from the intergalactic medium or from tiny, undetected satellite galaxies that may have merged long ago. The asymmetry isn't dramatic, but it's enough to suggest that NGC 2903 is not completely isolated, even if it lacks major companions. These minor irregularities may help stir the outer gas, keeping it from settling completely and promoting long-term dynamical evolution. In sum, the picture of NGC 2903 in radio wavelengths is one of deep complexity hidden beneath surface beauty. It reveals spiral arms extending into darkness, cold gas feeding the center, feedback pushing against gravity, and a vast, invisible halo maintaining galactic balance. It shows a galaxy not simply forming stars, but engineering them, drawing fuel from the edges, sculpting clouds into clusters, and exhaling matter back into its surroundings. The value of radio astronomy in this story cannot be overstated. Without it, NGC 2903 might appear as just another glowing spiral. But with it, we see the veins beneath the skin, the skeleton beneath the light, the circulatory system of a living galaxy. And as new generations of radio telescopes come online, like the Square Kilometer Array, SKA, the story of galaxies like NGC 2903 will only deepen, revealing not just how they shine, but how they live. In the vast expanse of the cosmos, galaxies are often not solitary wanderers but members of larger communities, groups, clusters, or pairs that interact, collide, and evolve together. The Milky Way, for instance, is surrounded by a bustling entourage of satellite galaxies, over 50 known companions, including the large and small Magellanic Clouds and dozens of faint dwarf spheroidals, all orbiting in our galactic halo. These companions interact gravitationally, tidally stretch, and in some cases even contribute material to their host galaxy. But when we turn our gaze to NGC 2903, a spiral galaxy not unlike our own, we find something surprisingly rare. It appears to be almost completely alone. Despite its size, mass, and structural complexity, NGC 2903 shows no confirmed satellite galaxies. This makes it a true anomaly in the galactic census. For decades, astronomers have scanned its surroundings using deep optical and radio surveys, hoping to find smaller companions, faint dwarf galaxies, HI-rich satellites, or tidally distorted remnants. And while a few possible candidates have been flagged, no object has been conclusively confirmed as a gravitationally bound satellite of NGC 2903. The galaxy appears to occupy its own patch of intergalactic space, relatively untouched by the gravitational fingerprints of neighbors. This isolation is intriguing, particularly given what we know about how galaxies grow. In the standard model of hierarchical galaxy formation, large galaxies like NGC 2903 are built through the merging and accretion of smaller ones. Over billions of years, a galaxy's halo becomes littered with the remnants of these encounters, streams of stars, shells of gas, or intact satellites still orbiting the primary galaxy. These companions act as both record and reservoir, offering insight into the host's history and future evolution. So why does NGC 2903 lack them? There are several possible explanations, none mutually exclusive, and all of them open doors to deeper questions about the diversity of galactic evolution. First, it's possible that NGC 2903 did have companions in the past, but it has long since absorbed them. Through slow tidal disruption and dynamical friction, a large galaxy can cannibalize smaller satellites, pulling their stars into its halo, their gas into its disk, and leaving only faint traces behind. In such a scenario, the absence of satellites today doesn't mean they never existed, it just means they've been thoroughly digested. If true, then deep imaging surveys of the stellar halo of NGC 2903 might yet uncover faint tidal streams, diffuse stellar shells, or metallicity anomalies that hint at long-gone mergers. However, as of now, such features have not been definitively observed. Another possibility is that NGC 2903 formed in a more isolated region of the cosmic web, away from dense clusters or active galaxy groups. This would mean fewer nearby protogalaxies to interact with or accrete during its early development. A galaxy formed in relative solitude may have grown mainly through smooth accretion of gas, rather than by eating its neighbors. If this is the case, it would make NGC 2903 a rare laboratory, an example of galaxy formation through internal processes rather than external disruption. Then there's the dark matter hypothesis. It's possible that NGC 2903 does, in fact, have dark satellites, small subhalos rich in dark matter but almost entirely devoid of stars or gas. These objects would be invisible in traditional surveys, detectable only through subtle gravitational effects like lensing or distortions in the velocity fields of surrounding HI gas. In recent years, simulations based on lambda-cold dark matter cosmology have predicted that many dark matter subhalos might exist without luminous counterparts, raising the possibility that the so-called missing satellites are there, but invisible to our instruments. A fourth possibility lies in the detection limits themselves. Faint satellite galaxies, especially low-surface brightness dwarfs, are incredibly difficult to detect. Even around the Milky Way, some of the most recently discovered satellites like Segway 1 or Tucana 3 are so dim they were missed until deep sky surveys like the Sloan Digital Sky Survey, SDSS, or the Dark Energy Survey, DS, uncovered them. If NGC 2903 has satellites, they may simply be fainter than our current instruments can reliably identify, especially given the galaxy's distance of about 30 million light-years. What appears as solitude may be, in part, a limitation of sensitivity. Still, even when we account for such limitations, NGC 2903's loneliness remains striking. Other galaxies at similar distances and sizes, such as M81, M101, or even M83, host visible satellite systems. Yet NGC 2903 continues to stand as a quiet monolith in Leo, shining alone in the void. This isolation has consequences. Without external galaxies to tug at its spiral arms or dump fresh gas into its halo, NGC 2903 evolves mainly through internal, secular processes. Its central starburst is likely driven not by collision or tidal disruption, but by the inward flow of gas along its bar, a self-regulating system of structure and star formation. This makes it particularly valuable to astronomers, who can study the physics of galactic evolution without the confounding influence of recent mergers. Ironically, its lack of satellites may help preserve its own structure. Spiral arms in some galaxies are warped or disrupted by interactions with nearby dwarfs. But in NGC 2903, the arms remain graceful, symmetric, and extended, suggesting a stable, undisturbed dynamical environment. Its stellar disk is relatively unperturbed, and its rotation curve is smooth, another indicator of its calm external history. And while it may not have companions, it does not drift aimlessly. NGC 2903 is still part of the Leo spur, a filamentary structure of galaxies within the local universe, though it resides on its outer edge. It's close enough to interact gravitationally with the cosmic web but far enough to have escaped the galactic rough and tumble of denser regions. It's like a mansion on the outskirts of a quiet cosmic suburb, still connected to the larger structure of the universe, but set apart from the din of galactic city life. In the end, the mystery of NGC 2903's solitude adds a layer of poetic irony to its nature. At the heart of this solitary spiral lies a roaring firestorm of stellar birth, a galaxy ablaze with activity, yet with no nearby neighbors to witness its brilliance. It is as if it burns for its own sake, sculpting stars from its inner chaos, pulling gas inward through self-gravity, and illuminating the darkness of Leo with its solitary light. It reminds us that the universe is full of contrast. Not every fiery center requires an external match to light it. Some galaxies ignite their own futures, alone, undisturbed, and all the more extraordinary for it. What makes NGC 2903 so compelling, so quietly remarkable, is not just what it is, but what it isn't. It's not chaotic, not the aftermath of a dramatic collision, not the smoking ruin of a galactic brawl. And yet it's alive, pulsing with energy, firing off stars like sparks from a furnace. While many other galaxies draw their activity from violent external forces, mergers, close encounters, tidal disruptions, NGC 2903 thrives in solitude. It doesn't need the disruption of another galaxy to awaken its heart. It is proof that activity doesn't require chaos, that even in isolation, a galaxy can be magnificently alive. This fact alone places NGC 2903 in rare company. The modern astronomical narrative often ties galactic transformation to interaction. Spirals become ellipticals through mergers, dormant galaxies are reignited by tidal encounters, and starbursts, those frantic episodes of stellar production, are frequently blamed on gravitational collisions. But NGC 2903 defies that mold. Located in the Leo constellation, far from densely populated galaxy groups, and with no confirmed satellite galaxies tugging at its edges, it presents a model of secular evolution, a galaxy changing from within. Secular processes are subtle. They work over long timescales, without the fireworks of collision. They rely on internal dynamics, such as the gravitational influence of a central bar, the slow migration of gas through the disk, and feedback from star formation itself. And in NGC 2903, all these mechanisms are on full display. The galaxy's stellar bar, a brilliant bridge of stars across its nucleus, acts like a gravitational engine, sweeping gas inward from the spiral arms and funneling it into the core. This slow but relentless inflow builds up the dense clouds that fuel the central starburst region, where stars are being formed at a rate far higher than typical spiral galaxies of its size. This kind of central activity, driven internally, is what astronomers call bar-induced starbursting. It's not explosive, it's persistent. Like a river gradually carving its way through stone, the bar of NGC 2903 shapes the galaxy's evolution without need for external disruption. It moves gas. It builds pressure. It sets the stage for birth and feedback. And perhaps most importantly, it keeps the cycle going. But while the mechanics may be internal, the result is no less dramatic. At the center of NGC 2903 lies a stellar furnace, a compact region churning out new stars at a frantic pace, generating heat, light, and shockwaves that ripple through the surrounding medium. The energy released from these young stars, through ultraviolet radiation, stellar winds, and ultimately supernova explosions, feeds back into the interstellar medium, driving turbulence and galactic winds, reshaping the surrounding gas. In other galaxies, such outflows are often triggered by mergers. In NGC 2903, they are born purely from the concentration of internal forces. And those winds don't stop at the center. Observations across multiple wavelengths, radio, infrared, optical, and X-ray, reveal layered outflows streaming away from the nucleus. Hot, ionized gas jets upward from the core, pushing against the halo. Cooler, denser clouds follow in slower waves, forming chimneys of matter reaching far beyond the visible disk. This behavior mirrors what's seen in galaxies undergoing dramatic interactions, yet here, no interaction is required. It's a solo act, powered from within. Even more impressively, NGC 2903 manages all this without becoming unstable. Many galaxies that experience bursts of star formation undergo dramatic morphological changes. They lose their disks, develop warps, or distort into tidal tails. But NGC 2903 maintains its elegant spiral symmetry, with arms that wrap smoothly outward, laced with glowing regions of starburst. Its disk remains well-ordered, its rotation curves smooth and undisturbed. It's a galaxy in dynamic balance, using internal pressures and gravity to regulate its own growth. That's not to say NGC 2903 is static. It's not. It's evolving. But it's doing so in a way that reflects the quiet power of internal mechanics, not the chaos of collision. Its spiral arms continue to sweep interstellar gas into dense clumps. Its bar continues to rotate, pushing gas toward the nucleus. Its halo, rich in neutral hydrogen, provides a reservoir that ensures this cycle can continue for millions of years to come. And this raises fascinating questions. What does a galaxy like NGC 2903 tell us about the life cycles of other galaxies? Could it represent a phase that all spirals pass through, one of self-sustained activity, between mergers? Or is it a cosmic outlier, an unusually balanced system that avoided disruption in a turbulent universe? The answers aren't fully known. But one thing is clear, it exists as a counterexample, a challenge to the assumption that major galactic evolution always requires major external events. In fact, its solitude may be the secret to its stability. Without companion galaxies tugging at its mass or triggering bursts of star formation, NGC 2903 has had time to develop its internal architecture without interruption. The bar could evolve slowly, the spiral arms could settle into their present form, and the central starburst could ignite not all at once, but as a gradual crescendo, a long-sustained, internally fed blaze. This has allowed astronomers to observe starburst behavior in its purest form, untainted by the messy complexity of mergers or close encounters. This is what makes NGC 2903 a cosmic laboratory. It isolates the variables. It lets us study bar dynamics, star formation, feedback, and gas flows in a clean setting, like watching a lone tree grow in an open field, rather than in a forest where roots and branches tangle. We can measure how a bar channels gas, how feedback regulates star formation, and how a galaxy builds its central bulge not through trauma, but through time. Every observation adds another clue to the broader puzzle of how galaxies evolve, not just through violence, but through endurance, balance, and internal design. And maybe that's the most remarkable part of NGC 2903's story. In a universe so often defined by collision and catastrophe, it is a beacon of self-contained brilliance. A galaxy that proves activity doesn't require destruction. That isolation need not mean dormancy. That in the silence of space, a galaxy can still roar. NGC 2903 holds a revered place in the hearts of astronomers not just because it is beautiful or dynamic, but because it is clarifying. In the noisy, chaotic cosmos where galaxies frequently twist and contort under the strain of gravitational encounters, NGC 2903 offers something rare, a clean case study. It is a galactic petri dish, a natural experiment unfolding 30 million light-years away, illustrating how secular evolution, slow, internal, non-collisional processes, can drive not just order, but extraordinary activity. For scientists probing the nature of galaxies, this makes NGC 2903 a laboratory in the sky. In astronomy, secular evolution refers to the long-term internal processes that gradually reshape a galaxy's structure. Unlike violent transformations caused by collisions or mergers, secular processes involve the redistribution of angular momentum, gas, and stars within a stable, isolated system. These include the slow buildup of bulges, the reorganization of disks, and the migration of material via internal features like bars and spiral arms. NGC 2903 exemplifies this entire suite of behavior. It is the textbook spiral galaxy, not only in form but in function, where the forces at work are clear, traceable, and largely unperturbed by external events. The starburst activity in its central region is what often captures the spotlight, but what fascinates astronomers is how that activity is internally sustained. Most classic starburst galaxies like M82 or NGC 253 show clear evidence of external triggers, either current or recent interactions with other galaxies. These encounters compress gas, destabilize disks, and flood galactic centers with material. But NGC 2903 tells a different story. There's no visible evidence of major interactions in its recent past. There are no tidal tails, no distorted satellites, and no interloping companions close enough to account for its behavior. Instead, it's the bar structure and internal gas dynamics doing the heavy lifting. The bar is crucial here. It's not just a visual feature, it's a dynamical engine. As it rotates within the galactic disk, it exerts gravitational torques on the gas in the spiral arms, drawing it inward along lanes of increased pressure and density. Over time, this continuous inward funneling builds up gas in the central kiloparsecs, increasing the density to levels where gravitational collapse becomes inevitable. Star formation then ignites, not explosively all at once, but in waves, regulated by feedback mechanisms from earlier generations of stars. This kind of starburst activity, triggered not by collision but by secular inflow, offers unparalleled clarity for astrophysical modeling. Astronomers can isolate cause and effect, study how specific structures like bars influence gas dynamics, and test models of galaxy evolution in an environment that's not muddied by complex merger histories. Every observation made in NGC 2903, whether it's in optical, infrared, or radio, feeds directly into a more nuanced understanding of how galaxies can evolve peacefully yet powerfully. Furthermore, because NGC 2903 is close and bright, it allows for high-resolution studies that would be impossible in more distant systems. Instruments like the Hubble Space Telescope, the Very Large Array, and the Atacama Large Millimeter/Submillimeter Array can resolve fine-scale structures, superstar clusters, molecular cloud filaments, and outflow cavities, in stunning detail. This means that theoretical models of star formation, feedback, and galactic inflow can be directly tested against real-world data. It's not just a pretty spiral, it's a system where the physics can be interrogated rigorously. Another major appeal of NGC 2903 is that it's not too extreme in any one direction. It's not an ultraluminous infrared galaxy. It's not a violently disturbed irregular system. It's not a quiescent disk either. It sits in a sweet spot, massive enough to be complex, but calm enough to be legible. Its dynamics, composition, and structure are all representative of what many spiral galaxies likely look like in isolation, making it a stand-in for countless similar systems across the universe. Its relative isolation also allows researchers to focus on how internal processes dominate its evolutionary path. Because there are no strong gravitational influences from nearby galaxies, the bar and spiral arms evolve under their own rules. Scientists can study how secular inflow develops over time, how spiral density waves regulate the distribution of gas and stars, and how these processes interplay with central star formation. It provides insight into the long-term fate of galaxies like our own Milky Way, assuming a future free of major mergers. The nuclear starburst at the center of NGC 2903 also provides an excellent testbed for studying feedback mechanisms. Star formation releases energy into the surrounding medium through stellar winds, radiation pressure, and supernova explosions. This feedback can either trigger more star formation by compressing nearby gas or halt it by blowing material away. Observations of the central region in X-rays and infrared show clear signs of outflowing gas and bubble-like structures, textbook signatures of feedback in action. Because these effects are driven internally, without the complicating factor of merger-induced shocks, researchers can study them with cleaner initial conditions. Even the dark matter halo of NGC 2903 is useful for research. Radio observations tracing the rotation of neutral hydrogen gas well beyond the visible disk show a flat rotation curve, a strong indicator of a dark matter-dominated outer region. Studying how this dark matter halo influences the motion of gas and stars helps astronomers refine their models of galaxy formation within the lambda-cold dark matter framework, especially for isolated systems. Lastly, NGC 2903 serves an educational role. Because it is so well behaved and so well studied, It is frequently used in textbooks, lectures, and university courses as a case study in galactic structure. Students learning about the Hubble sequence, bar dynamics, spiral density waves, or feedback-driven star formation can turn to NGC 2903 as a real-world example. It embodies these processes with such clarity that it becomes almost pedagogical, a teaching galaxy in the truest sense. In short, astronomers love NGC 2903 not because it is the most dramatic galaxy in the sky, but because it is a pristine example of elegant astrophysics in motion. It is a spiral galaxy with a starburst heart, powered not by violence but by symmetry, gravity, and time. A galaxy that evolves not with bangs, but with breath. It shows us that the universe doesn't always need to break things to build them. Sometimes, it just needs to let them move. One of the most powerful tools astronomers have for unveiling the invisible skeleton of a galaxy is the rotation curve, a graph that shows how fast different parts of the galaxy are spinning around its center. It's deceptively simple. Plot orbital velocity against distance from the galactic center, and a galaxy will begin to reveal not just its visible mass, but also the hidden matter that shapes its structure and governs its fate. In the case of NGC 2903, this curve doesn't just reflect the glow of stars and the swirl of gas, it also whispers the presence of something we cannot see, dark matter. To understand this, imagine watching a merry-go-round from above. The closer you are to the center, the tighter and faster the spin. The farther you move out, the slower things become. That's Newtonian physics. If a galaxy's mass were concentrated only in the center, like the Sun holding its planets, the outer parts would rotate more slowly, following the rules of Kepler's laws. But when astronomers plot the rotation curve of NGC 2903 using detailed radio data, particularly the motion of neutral hydrogen, HI, far beyond the visible disk, they find something very different. The rotational velocity doesn't decrease. It stays flat, and in some regions, it even rises slightly. This is not what Newton would have expected. It implies that there is far more mass out there than what we can account for with stars and gas alone. Something unseen must be exerting gravitational pull, keeping the gas orbiting at high speeds even in the outermost reaches of the galaxy. This is one of the most compelling pieces of evidence for dark matter, and NGC 2903 showcases it beautifully. Astronomers measure these rotation curves using a combination of optical emission lines from ionized gas and radio observations of cold hydrogen. The VLA, Very Large Array, has been instrumental in this regard, capturing the 21 cm line of HI gas with high spatial and velocity resolution. These observations extend far beyond the optical edge of the galaxy, revealing the motion of gas that lies in the outer, fainter regions, places where starlight grows dim, but rotation remains swift. Near the center of NGC 2903, the rotation curve rises steeply, which is expected. The mass is concentrated, and objects orbit quickly. But rather than peaking and falling off, the curve levels out at about 200 to 220 kilometers per second and holds steady out to distances exceeding 50,000 light-years from the core. This flatness indicates that the mass enclosed by the galaxy continues to grow with distance, even though the brightness drops off, suggesting the presence of a massive, extended dark matter halo enveloping the visible disk. What's particularly fascinating is that this rotation curve doesn't just provide a measure of dark matter's presence, it offers clues to its distribution. In NGC 2903, models that best fit the data indicate a cuspy dark matter halo, meaning the density of dark matter increases steadily toward the center, but not overwhelmingly so. It's not an exotic configuration, but rather one that aligns with lambda cold dark matter cosmological simulations, where galaxies form within halos of cold dark matter that provide the gravitational scaffolding for baryonic matter to gather and form stars. However, there's more nuance. Some high-resolution observations suggest that the actual distribution of dark matter in NGC 2903 may be less steep than predicted, especially in the inner regions, a finding that feeds into the long-standing core cusp problem in dark matter studies. This discrepancy challenges theorists to refine their simulations and perhaps consider alternative dark matter models, including warm dark matter or self-interacting varieties. The rotation curve of NGC 2903 also reveals interesting features in the disk dynamics. In the region where the central bar dominates, the rotation curve flattens in a way that reflects the complex interplay of stellar orbits, resonances, and gas inflows. These deviations from smooth circular motion aren't noise, they're data-rich indicators of the galaxy's internal structure. By modeling these regions carefully, astronomers can deduce the pattern speed of the bar, identify co-rotation radii, and estimate how efficiently the bar transports gas inward, fueling the central starburst. But dark matter isn't the only thing revealed by the rotation curve. By comparing the observed velocities with the distribution of visible mass, stars and gas, astronomers can also estimate the mass-to-light ratio of the stellar population. In NGC 2903, this value is relatively typical for spiral galaxies, suggesting a balanced mix of young and old stars. The curve also helps determine the total dynamical mass of the galaxy, which is estimated to be in the range of 1 to 2 times 10 superscript 1 superscript 1 solar masses, with only a fraction of that mass residing in stars. All of this makes NGC 2903 a benchmark system for rotation curve analysis. Its clean, symmetric structure, lack of disruptive companions, and rich HI envelope provide ideal conditions for studying galaxy dynamics without external contamination. It's the kind of galaxy where theoretical predictions meet observational precision, a proving ground for both cosmological theories and galactic physics. Even more compelling is how NGC 2903 invites comparison. Its rotation curve, when overlaid with those from galaxies like M33, NGC 2403, or our own Milky Way, shows remarkable similarities and subtle differences. These comparisons help astronomers understand how rotation curves change with galactic mass, size, environment, and history, offering insight into the diversity and commonality of spiral galaxy formation. Perhaps most importantly, NGC 2903's rotation curve reminds us that much of a galaxy's story is written in the dark. For all the brilliant stars and glowing nebulae, the true shape of a galaxy, its potential, its dynamics, and its ultimate fate, lies in the unseen mass that bends space and holds everything together. And through careful measurement of motion, galaxies like NGC 2903 allow us to read that invisible script, line by gravitational line. The spiral arms of a galaxy are among its most visually captivating features, elegant arcs sweeping outward from the core, sculpting the galactic disk into a grand cosmic whirl. But in galaxies like NGC 2903, these spirals are far more than ornamental. They are engines of transformation, fundamental to the way stars are born and gas is organized. To understand how this process unfolds, astronomers turn to one of the most enduring and widely accepted ideas in galactic astrophysics, the density wave theory. At first glance, one might assume that spiral arms are rigid structures, fixed patterns of stars and gas that rotate with the galaxy like the blades of a fan. But this isn't the case. If the arms were made of the same stars and gas moving together over time, they would wind tighter and tighter due to the differential rotation of the galaxy. The inner parts orbit faster than the outer parts. This winding problem would quickly destroy any spiral structure, making it impossible for arms to persist. So how do these arms maintain their graceful form over billions of years? The key lies in understanding that spiral arms are not fixed structures, but rather patterns of higher density moving through the disk, like traffic jams in space. In density wave theory, proposed by C.C. Lin and Frank Hsu in the 1960s, spiral arms are seen as quasi-stationary waves that propagate through the disk, compressing gas and stars as they pass. The individual stars and gas clouds move in and out of the arms over time, but the pattern of the arms remains relatively stable, like a wave rippling through water while the water itself moves in and out of the crest. Imagine a rotating disk with waves of enhanced density spiraling through it. As stars and gas approach one of these density waves, they experience a gravitational pull that slows them down slightly, causing material to pile up, much like cars slowing down as they enter a traffic jam. This increase in density compresses the gas, triggering conditions ideal for star formation. And just as cars eventually accelerate and leave the traffic jam, gas and stars move through the spiral arm and out the other side. What remains is the wave pattern itself, a spiral imprint of ongoing star formation, not a fixed cohort of objects. In NGC 2903, this process plays out across its bright, symmetrical arms, which are filled with hot, young stars, HI regions, and glowing nebulae, all evidence of active and recent star birth. These arms aren't just passively holding stars, they are sculpting them, using the gravitational resonance of the density wave to compress molecular clouds into the dense clumps necessary for gravitational collapse. And because these waves rotate more slowly than the material in the galaxy, they act as stellar birth zones, shepherding cold gas into bright clusters as the galaxy spins. The effectiveness of this process depends on the mass distribution of the galaxy and the pitch angle of the spiral arms, how tightly they wind around the core. NGC 2903's arms are moderately wound, forming a structure consistent with its classification as an SBDC galaxy, a barred spiral with well-defined but slightly flocculent arms. These arms likely emerge from resonances in the disk, locations where the orbital period of stars and gas matches the rotation of the spiral pattern. These resonance zones act as amplifiers, locking material into the wave and helping sustain the arm structure over time. Barred spirals like NGC 2903 add an extra layer of complexity. The central bar acts as a source of perturbation, feeding angular momentum into the disk and launching the spiral arms from its ends. These arms often emerge from the bar tips, where gravitational forces converge, helping seed the density waves that move outward. This linkage between bar and spiral structure is evident in NGC 2903, where the arms appear to spring organically from the bar's endpoints, forming a continuous dynamical system from the core to the outskirts. The composition of material within the spiral arms also supports the density wave theory. Observations across multiple wavelengths show that molecular gas, traced by CO emissions, tends to concentrate just upstream of the young stars, consistent with the idea that gas enters the wave, is compressed, and then forms stars. These stars, once born, move ahead of the wave, forming a trailing sequence of ultraviolet and optical emission, a timeline of stellar evolution frozen into the spiral structure. Moreover, shock fronts within the spiral arms play a crucial role in initiating star formation. As gas is compressed by the density wave, it often encounters shocks, abrupt increases in pressure that further accelerate the collapse of molecular clouds. These shocks can be identified observationally as regions where gas velocities change suddenly or where dust lanes are particularly dark and well-defined. In NGC 2903, the spiral arms are interlaced with such features, indicating zones of active collapse and energy transfer. The stars formed in these arms are not all identical. The spiral wave can give rise to a spectrum of stellar populations, from massive O-type stars that live and die quickly, to lower-mass stars that will persist for billions of years. The massive stars, though short-lived, contribute immensely to the evolution of the galaxy. They ionize nearby gas, creating bright HI regions. They generate intense stellar winds that sculpt the interstellar medium, and they end their lives in supernova explosions, enriching the galaxy with heavy elements and triggering further rounds of star formation. Over time, the material formed in the spiral arms disperses, populating the disk and contributing to the chemical enrichment of the galaxy. The arms themselves continue to ripple outward, undeterred, guiding new waves of gas into star-forming regions. In this way, NGC 2903 maintains a sustained rhythm of creation, not as a chaotic burst, but as a structured, regulated process governed by gravitational dynamics and fluid motion. Density wave theory also explains why we see older stars between the arms. As new stars form in the arms and then drift away, the interarm regions become populated with more evolved stellar populations, giving the galaxy its layered age distribution. In NGC 2903, the interarm regions are dominated by older yellow and red stars, while the arms themselves sparkle with blue-white youth, tracing the wave's path like glowing footprints across the disk. What's more, the density wave is not purely a two-dimensional phenomenon. In some galaxies, and likely in NGC 2903, vertical oscillations caused by the wave can create corrugations in the disk, ripples in the plane of the galaxy that further influence how gas settles and forms stars. These vertical motions are subtle and difficult to observe directly, but they may contribute to the overall regulation of star formation across the galactic disk. Altogether, NGC 2903's spiral arms demonstrate the intricate ballet of forces that shape galaxies from the inside out. These arms are not static. They are waves of compression and creation, moving through the galaxy like a heartbeat. Through them, the galaxy transforms cold gas into the raw energy of newborn stars. It is a process both majestic and mechanical, both chaotic and choreographed. And perhaps most stunning of all is that this grand process is driven not by some external hand, but by the galaxy's own gravity, an emergent pattern born from billions of stars moving in silent harmony, a blueprint woven into the very nature of rotating disks. In NGC 2903, we see that harmony laid bare, spiral arms in action, carving order from motion, and stars from gas. NGC 2903, a luminous spiral blazing alone in the constellation Leo, is more than just a galaxy. It is a time capsule, preserving within its graceful spiral arms and fiery core the subtle fingerprints of galactic history. Every star, every swirl of gas, and every ripple of dust in its structure whispers part of a story that has unfolded over billions of years. And for astronomers, it's a story rich with clues about how galaxies evolve, not through sudden drama alone, but through quiet persistence, symmetry, and the passage of cosmic time. To understand what NGC 2903 reveals about galactic evolution, we have to first recognize how galaxies like it come to exist in the first place. In the early universe, shortly after the Big Bang, the cosmos was nearly uniform, just a sea of hot gas, dark matter, and expanding space. But tiny fluctuations in density, seeded by quantum irregularities and amplified by gravity, began to grow. Over time, these denser pockets of dark matter collapsed under their own weight, forming dark matter halos, which would later become the scaffolds upon which galaxies would be built. NGC 2903 likely began as one of these primordial fluctuations, its dark matter halos slowly assembling through the merging of smaller halos in a process known as hierarchical accretion. At the same time, baryonic matter, gas and dust, began to cool and settle within this halo, forming the first stars and primitive galactic structures. Over billions of years, this process led to the emergence of a rotating disk, spiral structure, and eventually the bar that defines it today. But unlike many galaxies, which endured violent collisions or major mergers during their formation, NGC 2903 appears to have experienced a relatively quiet cosmic adolescence. This relative tranquility is key. Because NGC 2903 is isolated, with no known satellite galaxies and no signs of past major collisions, it allows astronomers to study the long-term effects of secular evolution, the internal processes that slowly reshape galaxies from within. By observing how gas is redistributed, how stars form over time, and how structures like bars and spiral arms develop and influence one another, scientists can piece together a vision of galactic evolution without the distorting effects of external trauma. One of the first major clues NGC 2903 offers is how angular momentum governs the formation and longevity of disk galaxies. The stars and gas in NGC 2903 move in a coherent, rotational pattern, an elegant dance that has lasted for billions of years. This rotation isn't just a side effect, it is foundational. Angular momentum, inherited from the initial collapse of the protogalactic cloud, prevents the system from collapsing into a spheroidal mass. Instead, the material flattens into a disk, a structure that promotes ordered motion and stable star formation. Over time, instabilities in this disk, driven by small gravitational perturbations, gave rise to spiral arms and eventually, the bar at the center. These structures are not static, but dynamic features that evolve slowly, interacting with gas and stars and influencing the rate and location of star formation. NGC 2903's well-formed bar and symmetrical spiral arms suggest a galaxy that has had time to refine its shape, developing complex internal dynamics that reflect its mature stage in the galactic life cycle. But maturity doesn't mean stagnation. The ongoing starburst activity in NGC 2903's core is a clear sign that this galaxy remains vibrant and active. Here, we see how evolution is not just about shape, but also about chemical enrichment. The stars forming today in NGC 2903 are being born into an environment already rich with heavier elements, oxygen, carbon, iron, created by earlier generations of stars and returned to the interstellar medium through stellar winds and supernovae. This metallicity gradient, which tends to decrease from the center outward, is a hallmark of a galaxy that has spent billions of years forming stars, recycling gas, and gradually altering the composition of its material. The balance between gas inflow, star formation, and feedback also offers insight into how galaxies regulate their own growth. NGC 2903 is particularly valuable in this regard because its isolation allows us to observe these feedback loops in a system that hasn't been externally perturbed. The inflow of gas along the bar fuels central star formation, while the energy from massive stars and supernovae heats and disperses some of that gas, creating a self-regulating mechanism that maintains equilibrium between star formation and gas supply. This interplay shapes not just the rate of star birth, but the future potential of the galaxy itself. Even the presence of a well-defined rotation curve, indicating a massive, extended dark matter halo, sheds light on long-term evolution. The stability of NGC 2903's disk over billions of years would not be possible without the gravitational support of this halo, which not only binds the galaxy together but also provides a framework within which baryonic matter can evolve. Observing how the visible galaxy interacts with this invisible halo helps researchers refine models of galaxy formation that include dark matter as an essential ingredient. The spatial distribution of different stellar populations within NGC 2903 also speaks volumes. Older stars dominate the central bulge and inner disk, while younger, bluer stars line the spiral arms. This age gradient is a snapshot of galactic memory, evidence that star formation has slowly migrated outward over time. It suggests a galaxy that has steadily evolved, building its outer regions long after the core had already matured. NGC 2903 even hints at the possible future of spiral galaxies like our own Milky Way. If left undisturbed, a spiral like this can continue to form stars at a moderate pace for many billions of years, gradually transforming gas into stars, thickening its disk, and growing a more prominent central bulge. Eventually, as gas supplies dwindle and internal evolution reshapes the dynamics, NGC 2903 could transition into a more quiescent state, its brilliant arms fading, its starburst slowing, and its light dominated by older, redder stars. This slow transformation, driven by internal processes rather than collision or collapse, is one of the quiet endings galaxies can experience, a graceful slide into stillness. By studying NGC 2903 in its current state, astronomers can essentially look forward in time, projecting how similar galaxies will evolve. They can also look backward, using NGC 2903 as a guide to reconstruct how stable disks form, how star formation propagates, and how galaxies maintain balance over billions of years. It becomes not just a case study, but a template for understanding galactic life cycles. In its structure, composition, dynamics, and ongoing activity, NGC 2903 reveals the long arc of cosmic evolution. It tells us that galaxies don't need violence to change. They can reshape themselves gradually, from the inside out. They can be both ancient and active, both structured and evolving. And in their quiet endurance, they show us a different kind of majesty, a majesty not born of chaos, but of cosmic patience. At the heart of most massive galaxies, including spirals like our Milky Way, lurks a colossus, a supermassive black hole, millions to billions of times more massive than our Sun. These gravitational titans sit silently in the center, not only anchoring the surrounding stars but also influencing the evolution of the galactic core over time. Naturally, astronomers have turned their attention to the vibrant, star-forming nucleus of NGC 2903 with a key question: is there a supermassive black hole at its center, too? It's a tantalizing prospect, especially considering the intense activity in the central region of NGC 2903. The galaxy's starburst core, already producing stars at a frenetic pace, seems to suggest the kind of environment where a central black hole might feed and flare, consuming gas and dust while emitting high-energy radiation. Yet surprisingly, despite decades of observations, no definitive detection of an active supermassive black hole has been made in NGC 2903. This absence of a clear signal doesn't mean the black hole isn't there. Instead, it speaks to a more subtle story, one of dormancy, concealment, or perhaps even youth. Detecting a central black hole isn't easy. The object itself emits no light. Instead, astronomers must infer its presence indirectly, either through the energetic outbursts it causes when actively accreting matter, as in active galactic nuclei or AGN, or by mapping the motions of stars and gas very close to the core, where the black hole's gravity dominates. In galaxies with luminous AGNs, this is relatively straightforward. The accreting material emits bright X-rays, radio waves, or optical lines that pierce through the dust. But in galaxies like NGC 2903, the black hole may be quiet, hidden behind layers of gas and stellar activity. Several studies have attempted to peer through that veil. Spectroscopic surveys of the nucleus have searched for the high-velocity gas motions and broad emission lines typically associated with AGNs, but the signals have been weak or ambiguous. The starburst itself complicates the picture. With so many massive stars, strong winds, and supernovae, the core of NGC 2903 is a noisy place, both literally and figuratively. The energy released by star formation can mimic or obscure the subtle signs of a feeding black hole. Still, some hints suggest there might be something lurking deeper. In the early 2000s, astronomers using Chandra X-ray Observatory data detected point-like X-ray sources near the center of NGC 2903. Some of these are likely X-ray binaries, systems where a stellar mass black hole or neutron star feeds on a companion. But one of the sources appeared to be more luminous and centrally located than the rest, raising suspicions that it might be associated with a supermassive black hole. The emission, however, was faint, much fainter than that seen in true AGNs. Later observations using infrared and radio wavelengths also looked for the telltale signature of a central engine. But again, the results were subtle. There was no bright radio jet, no distinctive core source beaming out of the nucleus. If a supermassive black hole does reside there, it's not making much noise, not now, at least. One possibility is that the black hole is starved. Even in a galaxy rich with gas, the environment immediately around the nucleus can be hostile to accretion. Powerful stellar winds from the starburst can sweep away material that might otherwise spiral into the black hole. Or, conversely, the black hole may already have cleared out its immediate surroundings during an earlier active phase, leaving itself with little to feed on. In either case, it could be lying in wait, dormant, invisible, but still exerting gravitational control over the stars around it. This brings us to another method of detection: stellar dynamics. If a supermassive black hole exists at the center of NGC 2903, it should cause stars in the immediate vicinity to move more rapidly. By measuring the velocity dispersion, how fast stars are moving and how that speed changes with distance from the center, astronomers can estimate the mass enclosed within a small region. If that mass is significantly higher than what can be accounted for by stars and gas alone, it likely points to a black hole. Such measurements require extremely high spatial resolution, typically achieved with instruments like the Hubble Space Telescope or powerful ground-based observatories using adaptive optics. Some studies of NGC 2903 have attempted this approach, though the starburst and dust make it challenging to isolate pure stellar kinematics. Results so far suggest a mass concentration in the central few parsecs, consistent with a supermassive black hole of perhaps a few million solar masses, in line with expectations for a galaxy of its size. This estimate is supported by scaling relations seen across the universe, such as the m-sigma relation, which connects the mass of a galaxy's central black hole to the velocity dispersion of its bulge. Based on the properties of NGC 2903's bulge, moderate in mass, typical for an SBBC galaxy, it would be reasonable to expect a central black hole in the range of 1 to 10 million solar masses. But whether it's there, and how active it might be, remains a topic of ongoing study. Another possibility is that we're witnessing NGC 2903 in a transition phase. Galaxies are dynamic, evolving systems, and their central black holes can switch between active and inactive states depending on the availability of fuel. Perhaps a few 100 million years ago, NGC 2903's black hole was active, briefly turning on as a low-luminosity AGN, before being quenched by feedback from the surrounding starburst. Or perhaps the current inflow of gas toward the center, driven by the bar, is slowly building up enough material for the black hole to reignite in the near future. In this view, NGC 2903 may serve as a snapshot of a dormant phase, an example of a galaxy where internal processes are hard at work shaping the nucleus, but where the black hole itself has yet to respond. It raises deep questions. Is the growth of the black hole lagging behind the growth of the bulge? Is it being suppressed by the very starburst it helped to trigger? Or is this galaxy simply one where the black hole remains modest, a quieter partner in a symphony dominated by stellar evolution? Whatever the case, NGC 2903's core remains a place of mystery. A fiery crucible of new stars, glowing dust, and turbulent winds, but perhaps also a silent well of gravity, holding secrets yet unrevealed. As future telescopes like the James Webb Space Telescope and the Extremely Large Telescope push the limits of infrared and spectroscopic resolution, they may finally unveil the truth. For now, we look to the center of NGC 2903 not with certainty, but with intrigue, wondering what force lies beneath the blaze. When we talk about starburst galaxies, the first images that often come to mind are those of dramatic, chaotic systems like M82, the Cigar Galaxy, or NGC 253, the Sculptor Galaxy, blazing furnaces of star formation with violently ejected gas and supernova-driven winds tearing through their disks. These galaxies dazzle with their frenetic energy, their brilliant cores glowing like galactic bonfires. But then there's NGC 2903, quieter, more symmetrical, and far less erratic. Yet, it too is undergoing a significant starburst, albeit in a more measured and internally driven way. The contrast between these systems is not just a matter of spectacle, it reveals important insights into the varieties of starburst behavior and the different paths galaxies can take to ignite the same essential cosmic process, the birth of stars. To begin the comparison, let's look at M82, one of the most iconic starburst galaxies in the sky. Located only about 12 million light-years away, M82 is undergoing an intense, concentrated starburst in its central region. Observations reveal hundreds of supernova remnants, dense superstar clusters, and powerful outflows of gas extending thousands of light-years above and below the galactic plane. These superwinds are driven by the combined pressure of radiation, stellar winds, and supernova explosions, and they light up the galaxy in X-rays, H-alpha emission, and infrared radiation. M82's starburst was likely triggered by a close interaction with its larger neighbor, M81, making it a textbook case of interaction-induced starburst activity. NGC 253, while not undergoing such a violent external encounter, also exhibits a dramatic central starburst. It lies roughly 11.4 million light-years away and is notable for its brilliant infrared emission, thick dust lanes, and streams of hot gas being blown into the surrounding halo. In NGC 253, the starburst is again concentrated in the nucleus, and radio observations show dense molecular clouds collapsing rapidly into clusters of young, hot stars. Like M82, it glows brightly across many wavelengths and is often described as a dusty maelstrom of creation. Now, compare this to NGC 2903, which resides at a greater distance of about 30 million light-years and presents a very different kind of starburst story. Its central region is also forming stars at a high rate, and it too hosts superstar clusters, supernova remnants, and outflowing gas, but everything about its starburst appears more regulated, more disciplined. There are no massive plumes of expelled gas extending into space like in M82. There's no evidence of a recent galactic collision, like in NGC 253. Instead, the central activity in NGC 2903 seems to be self-driven, resulting from secular evolution rather than cosmic violence. One of the major differences lies in the trigger mechanism. In extreme starburst galaxies like M82, gravitational interactions disturb the galactic disk, funneling enormous amounts of gas into the nucleus. This rapid inflow fuels an explosive period of star formation and often activates the central supermassive black hole, transforming the galaxy into a powerful active galactic nucleus, AGN. But in NGC 2903, no such interaction is apparent. Its bar structure, a stream of stars crossing the central bulge, is the main engine transporting gas toward the core. This bar-driven inflow is slower, more continuous, and more stable, allowing the galaxy to maintain a long-lasting, sustained starburst rather than a sudden, brief outburst. In terms of star formation rates, NGC 2903's central region is vigorous but not extreme. Estimates suggest its central starburst is producing stars at a rate of 1 to 2 solar masses per year, focused in a region only a few thousand light-years across. Compare that to M82, where the rate can reach 10 or more solar masses per year in the same area. And in NGC 253, star formation is also much more intense per unit volume. NGC 2903's more moderate rate allows it to avoid some of the destructive feedback seen in those galaxies, where radiation and explosions can blow out or heat up the gas, halting further star formation in bursts and surges. That's not to say NGC 2903 is completely calm. It does show evidence of galactic winds in the form of warm gas streaming outward from the core, and it has likely experienced episodic bursts of star formation in the past. But the outflows are not as extensive, and the structure of the galaxy remains intact, suggesting a more balanced feedback loop. In this way, NGC 2903 may represent a more sustainable mode of starburst activity, an internal equilibrium between gas inflow, star formation, and feedback that allows the galaxy to remain active over longer timescales. The dust content and infrared emission also provide clues. In M82 and NGC 253, thick dust obscures much of the core in optical light, requiring infrared observations to peer into the heart of the action. NGC 2903 does contain significant dust, but not at levels that entirely shroud the core. Its central region emits brightly in infrared, thanks to warm dust heated by young stars, but it's less optically opaque, allowing a more complete multi-wavelength view of the starburst processes underway. From a structural perspective, NGC 2903 also differs in its morphological harmony. Its spiral arms are symmetrical and orderly, and the galaxy as a whole maintains a classic barred spiral form. In contrast, M82 is warped and distorted, with no prominent spiral arms, and NGC 253, while more coherent, shows asymmetries likely caused by interactions with smaller companions or internal disk instabilities. These differences in structure reflect the underlying causes of their starbursts: chaotic in M82, semi-chaotic in NGC 253, and structured in NGC 2903. This makes NGC 2903 incredibly valuable for comparison. It occupies a middle ground, not as sedate as galaxies in quiescent phases, but not as turbulent as the most extreme starbursts either. It gives astronomers a glimpse into what a non-interacting, bar-driven starburst looks like. This matters greatly for understanding galactic diversity. Not all starbursts are the result of collisions. Some are born from the internal reshaping of a galaxy's own mass and momentum, a long, slow funneling of gas inward, followed by a luminous phase of activity and enrichment. It also hints at a different fate. M82 and NGC 253 are consuming their gas rapidly. Their starbursts may not last more than a few tens of millions of years. But NGC 2903, with its lower star formation rate and gentler feedback, may continue forming stars in its center for hundreds of millions of years. It's a marathoner among sprinters, a galaxy playing the long game. In this context, we can think of NGC 2903 as a cosmic analog to sustainable growth, in contrast to the explosive, short-lived booms of its more violent counterparts. It reminds us that not all transformation requires upheaval. Some of the most luminous processes in the universe, like the birth of stars, can be ignited not by external forces, but by the steady hand of internal structure, orchestrating a quiet blaze from within. Though NGC 2903 is among the brighter galaxies in the night sky, especially for one not listed in the famous Messier catalog, it poses a unique challenge for amateur astronomers and even some professional instruments. You might expect that a galaxy of such apparent magnitude, lying in the easily accessible northern sky, would be a staple in every backyard observer's notebook. Yet many skywatchers overlook it or find it underwhelming through small scopes, not because it's dim, but because of a complex interplay of brightness, surface detail, and location that conceals its true splendor. Let's start with the illusion of brightness. On paper, NGC 2903 has an apparent visual magnitude of around 9.0, easily within the reach of modest amateur telescopes. However, brightness alone doesn't guarantee visibility. That figure represents the integrated magnitude, meaning the total light from the entire galaxy is concentrated into a point for measurement. But NGC 2903 is extended, spanning nearly 12 arc-minutes across the sky. That's about the same apparent size as a third of the full moon. So instead of all its light being packed into a small, easily visible point, it's spread out across a relatively large area. This makes the surface brightness, the brightness per square arc-minute, significantly lower than its magnitude suggests. What looks like a bright galaxy on paper can turn into a faint smudge in practice, especially under light-polluted skies. The details that make NGC 2903 fascinating, the bar, the spiral arms, the central glow, require good contrast to discern, and contrast is what urban skies rob most enthusiast observers of. Another challenge is NGC 2903's position in the sky. It resides in the constellation Leo, which is a familiar springtime fixture in the northern hemisphere. Leo itself is easy to find, with its sickle-shaped head and bright stars like Regulus, but NGC 2903 is located just below the lion's muzzle, near the star Lambda Leonis. This area of sky, while decently high in altitude for northern observers during March and April, is also bordering the ecliptic, the path the moon and planets follow. That means the region is more prone to interference from moonlight and zodiacal light, further reducing the galaxy's visibility during crucial observing windows. To complicate things more, NGC 2903 lacks the dramatic visual cues that draw attention to other popular galaxies. It has no stark dust lanes like M104, the Sombrero Galaxy, no vast companion galaxies like M51, the Whirlpool, and no giant elliptical core like M87. It's symmetrical, yes, but its beauty is in subtlety. To most visual observers with smaller telescopes, say, 4 to 8 inches in aperture, it may appear as a faint elliptical haze, maybe with a brighter core if seeing conditions are ideal. The spiral arms and central bar that define its structure only become visible in larger scopes, 10 inches and above, or with long exposure astrophotography. Indeed, this is where NGC 2903 begins to shine, in photographs. Long exposures with DSLRs, CMOS sensors, or CCD cameras reveal the galaxy's full grandeur, the twisted spiral arms glowing with hot blue stars, the golden bar streaming across the center, and even the diffuse extensions of gas and halos stretching into the background. Amateur astrophotographers who take the time to stack and process deep images often discover that NGC 2903 is one of the most picturesque non-Messier galaxies in the spring sky. But even in astrophotography, NGC 2903 isn't without its obstacles. Unlike galaxies in more isolated parts of the sky, it sits in a region that can be dense with background stars, especially when imaging at lower focal lengths. This stellar noise can make it harder to isolate the galaxy in post-processing. Also, the diffuse outer regions, where the neutral hydrogen halo and extended arms fade into the cosmic background, require longer exposures and excellent tracking stability to capture. For those without equatorial mounts or auto-guiding systems, this means it's easy to underexpose the galaxy and lose much of its detail in the blackness. There's also the issue of atmospheric seeing. Though NGC 2903 is high enough in the sky during Leo's culmination to avoid horizon haze, springtime skies can often be unstable, with high-altitude turbulence or shifting air layers that blur detail. This affects both visual observing and imaging. In regions with high humidity or pollution, even a reasonably dark location might not offer the sharp contrast needed to tease out its spiral details. Another factor working against the casual observer is the lack of fame. Since it's not in Messier's catalog and not commonly featured in beginner observing guides, NGC 2903 is often overlooked in favor of brighter, more celebrated targets. This leads to a feedback loop. Fewer amateur astronomers focus on it, so fewer images and recommendations are shared in forums, making it even less likely to be explored. Yet for those who seek it out, especially under dark skies with the right equipment, it offers a rewarding view into a galaxy alive with subtle detail, a dynamic hub of star formation that simply doesn't shout for attention. One more thing worth noting is the difficulty in visualizing motion or structure in a galaxy like NGC 2903 through a telescope. Because we see it face-on, its rotation isn't obvious to the naked eye or even in a typical photograph. Without a strong edge-on perspective like that of M82 or NGC 4565, we don't get the visual thrill of seeing a flat disk slicing through space. Instead, we must rely on deeper interpretation, through data, models, and enhanced imaging, to appreciate the dynamics at work. Despite all this, NGC 2903 continues to be a favorite among dedicated deep sky observers. Those who track it down during Leo's reign and spend the time to adapt their vision to its faint glow often describe it as a ghostly swirl, quietly elegant and endlessly layered. It's not a showpiece galaxy, but it is a revealing one, especially to those who dig deeper. Perhaps, in some poetic way, this difficulty mirrors the nature of NGC 2903 itself. Just as its starburst core is hidden behind veils of dust and infrared glow, just as its galactic winds are subtle and confined, its observation, too, requires patience, persistence, and a willingness to see what others overlook. Far beyond the city lights and the clamor of nearby stars, nestled in the calm heart of the constellation Leo, NGC 2903 spins in silence. It is not the loudest galaxy, nor the largest, nor the most chaotic. But it is alive, a galaxy that burns not with explosive violence, but with a quiet, determined flame. In a universe so often defined by cosmic collisions and cataclysmic change, NGC 2903 is a reminder that there is majesty in persistence, in internal transformation, and in slow, powerful growth that no eye sees and no textbook canonizes. This barred spiral, barely a footnote in many skywatchers' lists, carries within it the story of what a galaxy can be when left to its own devices. No nearby companions jostle it. No recent collisions have distorted its shape. Its spiral arms are not frayed with the drama of interaction, but rather wrapped around the core like the gentle folds of a galaxy that knows its structure. And yet, within that calmness it glows, a furnace of creation at the center, fed by a bar of stars and rivers of gas that spiral and like dancers moving toward a single point of light. NGC 2903 isn't just a place where stars are born. It's a place where the universe itself is writing poetry, star by star, cloud by cloud. There's an elegance to the way its core shines in infrared, invisible to the human eye but picked up by our far-seeing instruments. There's a richness in the way its cold hydrogen halo surrounds it, like a reservoir of future dreams waiting to ignite. And there's meaning in the fact that, even without fame or fanfare, this galaxy continues to teach us about balance, about evolution without violence, about power and stillness. As our own Milky Way sails through space, guided by its own bar and spirals, it is not unlike NGC 2903. And perhaps, billions of years from now, when the sun is long gone and our galaxy's spiral arms have faded into wisps of starlight, someone, or something, else will look up from their own world, find NGC 2903 in the Leo sky, and see a spiral much like their own. A distant echo of what galaxies were. A time capsule. NGC 2903 doesn't shout. It whispers. And if you listen closely, in the infrared shimmer and the slow-turning rotation curve, in the silent outflow of gas and the gentle roar of supernova winds, you can hear it telling the universe, I am here. I am alive. I burn, not to be seen, but because that is what I was made to do. In a sky full of fireworks, NGC 2903 is a quiet blaze, steady, beautiful, and eternal. And maybe that's the most awe-inspiring kind of galaxy there is. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.